Good afternoon and welcome to today's session. Today we have with us for the invited talk Professor Karthikeyan Bhargavan from India, Paris. And for this session, we have two session chairs with us, Professor Larth Kuster and Dr. Jai Prakash Kaur. So we welcome you all and over to you to the session chair. Thank you.
Thank you very much. So welcome everybody to the last day of Indocrypt. As usual, we start with an invited talk, and it's my great pleasure to introduce Dr. Karthik Bhargavan as today's invited speaker. Karthik is a research director at INRIA Paris, and with no doubt, one of the leading researchers in the field of tool-based verification of cryptographic protocols. And more generally, his research lies at the intersection of programming languages, software verification, and applied cryptography. So Karthik not only analyzes abstract models of cryptographic protocols, but actually looks at their implementation, and he also produces verified protocol implementations. So he has developed and also co-developed many influential verification methods and tools and used them to analyze highly security-critical protocols which are really at the heart of today's security infrastructure. For example, he has been heavily involved in the analysis of TLS, discovered many attacks on TLS like Logjam and Freak and others, and has helped to improve the new TLS 1.3 standard we all rely on. So Karthik has received many prestigious awards, and really too many to mention them all. For example, the Lifshitz Prize for Real-World Cryptography and the Horizon Impact Award of the European Commission. So without further ado, welcome with me Dr. Karthik Bhagavan. Karthik, the floor is yours.
Thank you so much, Ralph. Thank you so much for those kind words. So today, I'm going to be presenting some work which is in collaboration with many, many other authors at INRIA, Microsoft Research, Carnegie Mellon, and the University of Stuttgart, including Ralph himself. And the theme of the talk today is high assurance and high performance crypto software. Okay. So what I posit is that we are in what I think of as a golden era for the design and deployment of new crypto schemes, new crypto software. What do I mean by this? Well, every website today has to implement HTTPS, which means it's using cryptographic protocols like TLS, QUIC, and ACME underneath it. Every person in the room and on Zoom is definitely using multiple secure messengers, including Signal, WhatsApp, Skype, whatnot. And of course, we all hear a lot about, and perhaps too much about, cryptocurrencies of various kinds. But that's just the state today. And there's a lot more coming on, right? There's like new post-quantum crypto schemes that are being standardized right now, lightweight crypto schemes, multi-party computations, for fully homomorphic encryption. All of these are coming out from research into the light of day and slowly but surely getting widely deployed. So these are all the exciting things happening, right? But let's go back to something which is very boring. The quintessential cryptographic software, which is so boring that we don't even think of it as cryptographic software, is your web browser. So this morning, I went to my SBI account, and this is the page that comes in front of me, right? It asks me to put in my username, password, captcha, it'll give me an OTP, and it tells me, be vigilant, be safe, and allows me to get into my bank account. So what gives me the confidence to access this account, do my transfers, and these kinds of things? It's the little lock on top, right? And if I kind of dig into the little lock in the Firefox developer console, what I'll see is that, well, that lock basically means that we're using HTTPS, which means there is a secure channel between my browser and the bank. And the secure channel is implemented using TLS 1.2, which internally uses an Diffie-Hellman construction, a signature construction, and authenticated encryption construction, notably NIST P256 for Diffie-Hellman, RSA for signatures, and AES-GCM for encryption. So this gives me a lot of details. But how exactly does it work, right? And if I try to give you a high-level idea of how TLS 1.2 works, and in fact, this is how TLS from the time it used to be called SSL in 1994, all the way till it was TLS 1.2 until to 2017 even used to work, is very, very simple, okay? So the protocol is on the right. You and I could have probably written this protocol in the 1980s, definitely by the 1990s, and nobody would be surprised. So the browser sends a nonce, the server creates a Diffie-Hellman key share G to the power Y and signs that along with a couple of nonces. The client then sends its own Diffie-Hellman key share G to the X. Both parties can compute G to the power XY and derive a key from this. And this is the key we are going to use to encrypt data in both directions. So if you look at that protocol, it's a very classic secure channel construction. It's an authenticated key exchange followed by authenticated encryption. There are many variations of this, but really, this is like very well studied. There are many, many proofs. In fact, most of the protocols in the IETF, including IPsec and TLS, were all inspired by Sigma, which was developed and proved and settled in 2003. Which means that by the time TLS 1.2 came out in 2008, this, for many people, was considered a solved problem, at least cryptographically, from the design point of view. This is classic, this is solved, this is verified in many different ways. Except it isn't, right? Between just the 5-year zone I'm looking at here, and this is not even an exhaustive list, between 2011 and 2016, This is a subset of the attacks with names, logos, and high-profile news articles that were made on TLS deployments. So there was this beautiful high-level protocol with many security proofs. And then there are these deployments with like these bazillion attacks. So what's going on? What is this gap between the theoretical protocol and the realistic deployment that is giving rise to all these attacks? It's worth digging into this before we decide how we can improve the situation. So what goes wrong between this high-level protocol and the low-level implementation and deployment? Well, in order to take your nice theoretical design and get it into production, there are many steps you have to go through. The first one, which I'm afraid I insist my students do, but many of us don't, is to say, well, you can't just give me a protocol without telling me what algorithms you're going to use, right? Let's instantiate all the crypto constructions in your protocols with the concrete crypto algorithms you're going to use, which means you also have to make some high-level choices, like what kind of key exchange should I use? Shall I use a post-quantum chem because it's really cool? Or shall I use ECDH because that's now widely deployed? Should I use for authentication a signature scheme, or shall I use a pre-shared key because that would be much faster? For authenticated encryption, well, of course, today it's pretty much settled. You should use some kind of AEAD scheme. But even then, how do we generate the norms for the AEAD scheme? This is not really clear, and each protocol makes its own decision about this. So you have to make these decisions about how you're going to instantiate and use the crypto algorithm to implement your protocol. And there are many, many possibilities, dozens of possibilities. Each of them has subtly different security guarantees. And there are many ways of getting it wrong. And that accounts for about half the attacks on the list I showed you before, which is that there were some broken, outdated crypto algorithms being used, and they shouldn't have been used, at least in that form, in that protocol. Okay, so now you have fixed all the crypto algorithms. What's the next step? Well, the next step is that you want your protocol to be used by many different people. So you want an interoperable protocol standard. So you want to have a document which anybody can read and implement, right? Otherwise, you'll have only one implementation, which might be okay in certain niche cases. But for a protocol like TLS, you want to have a standard which everybody can follow. It's well documented. And the standard is much more than the tiny little figure I showed you. First of all, you have to fix all your message formats. So all the messages, including the things you're going to put inside signatures, inside encryption, have an unambiguous formatting. And this is important for security. Otherwise, you could take a signature meant for one purpose and actually send it where a signature was expected for a different purpose, and this would be an attack. It may not appear in your high-level model, but it certainly will appear you'll have to account for it in your standard. And then you might want to have agility in your standard. You might want to support different kinds of authentication modes, different kinds of cipher suites. And this, again, is important because of the politics of the thing. One company might prefer this algorithm, another company might prefer a different algorithm, and you might have to support both in your standard. And the third one, which is somewhat boring, and it's important for protocols like TLS, but maybe not important for a brand new protocol you design, is backwards compatibility. So when you're designing something today, it's version 1, so you can make it perfect, of course. But 10 years from now, you are going to want version 2. And when you have version 2, you shouldn't regret that when you were designing version 1, you didn't already design it in a way that you could extend it later. And when you're extending it later, you want to be backwards compatible with earlier versions. And this introduces a lot of complexity. So as a result, the published standards of protocols, even if the high-level protocol was just a very simple one like I showed you, ends up being hundreds of pages. And of course, in the corner cases of these protocols, there are going to be problems like downgrade attacks, where you have 2 versions and somebody can downgrade you from a higher version to a lower version, or a key synchronization or an unknown key share attack, and many such things. And that accounts for a few of the attacks that I showed you between 2011 and 2016. But perhaps the largest chunk of problems and attacks that you see in the real world does not even come from those 2 stages. It comes from the last stage. So you have your beautifully specified protocol standard or document, well, clearly defined. You've solved all the problems of design, but now you have to implement this, right? And when you're implementing this, often a big consideration is you want to deploy it on multiple platforms. And a second consideration is you want it to be fast. Because protocols like TLS in particular, but also VPN protocols, many other kinds of protocols are in fact a performance bottleneck in many systems. This is true in embedded systems where crypto takes most of the time of execution for many of these embedded systems. It's also true for massive server farms like Google and Akamai and Cloudflare, where in fact a large chunk of the server processing is in fact in TLS. So you really need to optimize this, which means that you need to have a crypto library that is high performance crypto for multiple platforms. When you're doing message processing and parsing and serialization, you have to be careful to do zero copy parsing and so on. You have to figure out where you're storing your keys and how you're managing your keys across these multiple servers which might be sharing these keys. And then you have to also, of course, implement the protocol state machine, which has to compose all the sub-protocols in the right way without any confusions. And all of these are problematic and error-prone tasks. Okay, this is not a very easy task to do. And each of these has many, many CVEs in the last few years where people have gotten them wrong. And at the end of this, you end up with a large code base, which is supporting multiple versions, multiple cipher suites, but also has to be super efficient on every single platform. So you have like different variants and code paths for different platforms. And of course, this is going to result in bugs. So at the crypto layer, the kinds of bugs you see are correctness bugs, memory safety bugs, side channel bugs all over the place. And at the protocol layer, you see problems in terms of how people confuse the state machine and therefore can bypass completely the protocol, or there could be a parsing bug like heartbleed that leads to devastating problems, right? So these are the three stages of going from a high-level protocol all the way down to the software that's eventually deployed. And at each stage, you can see that there are many things that can go wrong. So going back to our original thought that we are in a golden era for the design and deployment of new crypto stuff, we also have to temper that with the knowledge that whenever we are designing and deploying new things, many things can go wrong, and they do go wrong between our beautiful theoretical design and the real-world deployment. And this is our responsibility, as designers, as cryptographers, as computer scientists. We have to think not just about the thing that we're going to put in our paper, but how it's actually going to be used. And to this end, there is this field of research, which is sometimes called computer-aided cryptography, where the goal is to build tools and techniques by which we can take the same level of assurance we expect for a theoretical protocol, like the provable security guarantees we expect in theory, and try to push them as far down the stack as we can, all the way to the implementation. Sometimes you can go all the way down to assembly even to give you the same kind of guarantees that you got from this beautiful 5-line protocol that you wrote a game-based proof for. So in the rest of the talk, I'm going to try to give you a flavor of what can be done today. What are the open problems? What are the closed problems? Not closed necessarily, but somewhat solved problems. And how can we use formal methods to build fast, verified crypto protocol implementations, which is what people need in practice. So rather than try to tackle TLS, which as I said already is kind of this boring web browser protocol, let's take the coolest example of crypto protocol that we are all using, right? So the cryptographer's favorite messenger, which is Signal, or at least it should be if you're not using it. So Signal is a phone app, and it does end-to-end encryption, and it guarantees that you don't have to trust the server, right? So that's sort of the selling point of it. And if you look under the hood, Signal has a very innovative protocol design. It's much more innovative than TLS. We'll see a few details of this protocol later. In particular, it first has a first phase, which called X3DH, where you establish the initial key. There's a second phase where you keep renewing the key to get this interesting property called post-compromise security. And then there is the third phase where there's a third layer of spec where you manage all the sessions that you have open. So it has detailed documentation. All the code is open source. There are many academic analyses of this protocol. It's not just used in Signal Messenger. It's also used in WhatsApp uses this, Skype uses this. Many other products use the same protocol. So it's really become a kind of a de facto standard in the messaging space. So this seems like an ideal candidate for a high assurance implementation, right? So all of us are using, whenever we want to send secure messages to each other, we would like to use Signal. Can we prove that the Signal Messenger, which is using all of these interesting crypto things, is secure all the way down to its implementation? To answer this kind of question, we must first unpack the implementation. So if you actually unpack the Signal app and look at what is there inside its components, what makes up the Signal iOS app that is on the iPhone, the Android app is very similar. You'll find that, in fact, about 1% of this code is crypto. Okay, About 2% of this code is protocol code, 7% is key and session handling, how to manage keys, how to manage sessions, and about 90% is really UI, okay? And this is not such a surprising breakdown. I would say that any security-focused app like Signal would have a similar kind of breakdown. If you take a web browser, of course, the UI app code is much larger. It's millions of lines of code, and the crypto code is much smaller. If you go down towards an embedded system, in fact, the crypto code seems much larger because the app code is much smaller. So, but in this domain of security-sensitive apps, this is pretty typical. So there's two kinds of news we can take from this. The first is, you might say, well, great, we only need to verify 10% of the code, 30,000 lines. Even though Signal itself is 300,000 lines, only 30,000 lines of it is really security critical in the sense that it touches the keys and secrets and stuff. The slightly negative way of looking at it is that, yes, but any bug in the other 90% can still break security. And that's because this is written in Objective-C, where there is not really any strong boundaries between the trusted or crypto code and the rest of the application. But let's be optimistic and let's try to focus on this code that we want to verify. So suppose you took the application code for something like Signal, and let's identify these 4 contents. There is a session API, there's key management, there's messaging code, and roughly the top 3 boxes together are thought of as the protocol implementation. And then there's a crypto library that actually does the crypto algorithms. So what we could do is try to write formal specifications for each of these layers and verify. So for the crypto library, usually there's a nice mathematical spec in some paper that we can take and we can say, okay, this crypto implementation, even if it is written in C and assembly or whatever to be really fast, really is computing this mathematical function. So we can try to write that spec. For the messaging code, we can take the protocol standard and extract a spec out of it and say, okay, this messaging code is actually implementing this protocol, which is the TLS standard or the Signal X3D8 standard or whatever. Then when we go up towards the session API and key management, usually there is no documentation, there is no standard. Every application does its own thing. But the application designer, one might expect, can write down a spec for what they expect should be, how sessions should be handled, how keys should be handled, what the security goals there are, and there might be some spec we can write there. And once we have a spec for what is supposed to happen in these cases, a formal specification, we can try to use some tools to verify that this code, which is really written for efficiency and deployability, matches this high-level spec. And if it doesn't, maybe it means there's a bug, maybe it means there's an attack. Okay. So the kinds of questions you want to ask here are actually twofold. The first, does the code on the left match the spec on the right? But then second question you want to ask, does the spec on the right imply security? So if you write code that meets the spec, can we prove that then it will actually guarantee the security goals that we expect from this application? Okay. So we're going to ask and answer both these kinds of questions over here. So of course, the first question you might ask is, well, okay, you said you're going to verify the security core. Well, how can you be sure that the rest of the application is not going to mess you up? We don't have very good answers for this. This is still an open challenge. There are some answers in some languages. You can say, oh, I'm going to use type-based abstractions. I'm going to use defensive programming. Or there might be some architectural solutions, like I'm going to use an enclave to put the crypto code inside it. Or I'm going to use some kind of secure compiler which provides isolation guarantees. But considering that most of the code that is deployed out there is in languages like C and Rust and assembly, you really don't get any strong isolation guarantees. And isolating out the trusted or verified code from the untrusted or unverified code is still an open challenge. So let's focus first part of the talk on this lower layer, on how to verify the crypto library against its mathematical spec. Is the crypto correct? So how does one implement crypto, right, in practice today? So you start from some kind of spec that has been given to you by the NIST or IETF or something like that. And then you, so here is the Cha-Cha-20 Poly 1305 spec from the IETF. It's a couple of years old. And then you go inside this spec and you find some pseudocode. And this is usually written in some Python-like syntax in most of these specs. Some of them use slightly different syntax, but some kind of pseudocode. And looking at that pseudocode, you can try to implement it in some language like C. And for ChaCha20, you can implement it in about 100 lines of code. It's pretty compact and small. It's portable, 32-bit C. It will run on any platform you can think of. And it's reasonably fast. I mean, it takes about 4 to 9 cycles to encrypt a byte on a relatively modern machine. So you could just use that and you're done. So the crypto has been implemented. But of course, that's not good enough because your laptop on which you're seeing this or on which I'm presenting actually supports SIMD vectorization, which means single instruction, multiple data parallelism, which means I can actually process 8 blocks of ChaCha at the same time. Okay. So if I can do that, I can get 5x speed up, right? So of course I want to do that, right? So what most implementations do is also have a assembly implementation of ChaCha20, which looks something like this, which uses exactly the instructions that are available only on Intel AVX2 compatible machines, which are like modern laptops and desktops. But hey, you have a phone which is running Android on an ARM chip. And you might say, oh, then I will not get that speed up. But no, ARM also offers its own instruction set called ARM Neon, which can speed up by doing 4 operations in parallel. Okay, so then you would have a third implementation, which uses assembly for ARM, which does, in case somebody is using this on a smartphone, so that they can do this about 2 to 3 times faster than the C implementation I showed you. And each of these speed ups is actually critical. I mean, without these speed ups, you would not be able to use things like Signal and TLS on your cell phone. Okay, and then of course every year it changes. So this year, all the laptops coming out from the Intel stable support AVX512. All servers support AVX512, which means now we can do 16 operations in parallel and get 10x speed up. So this is a never-ending kind of evolution where we are going to keep getting new and new platforms which provide different kinds of instructions, different kinds of speed ups. So people are going to keep implementing these things in different languages and provide multiple implementations. So before you know it, even just for ChaCha20 Poly 1305, which is just one algorithm, you end up with 20,000 lines of code in OpenSSL and Boring SSL because they have code for every single. Otherwise, can we be sure that all of this code is correct? Because there could easily be buffer overflows here. There could be timing leaks. There could be arithmetic bugs. And every year, there are many of these. So there are many CVEs and many libraries which are exactly in these 3 categories. Because someone did not test enough the PowerPC version of ChaCha20 Poly 1305 on 32-bit machines, because it's kind of a corner case and there's a bug there. It may be a corner case for this algorithm, but of course, for the person using PowerPC, this is actually a critical bug. So there is an answer, which is formal verification. So instead of going from the pseudocode directly to your implementation in C or assembly or Rust or whatever language you're writing your code in, you first should develop a formal spec, which is derived from the standard, and prove that this formal spec meets your implementation. And in this verification, you can prove things like, yes, my code is correct. Even if it's this fancy optimized assembly code, I can prove that it is actually implementing this high-level mathematical function, which is functional correctness. You should also prove that you're never accessing memory outside your bounds, which is memory safety. And you can prove things like secret independence, which means that I'm never going to branch on a secret. I'm not going to access a memory, an array with a secret index. So to enforce this, what they call constant time coding discipline on the crypto code. So this kind of thing you can verify using a variety of tools. For C, I'm going to show you a tool called Hackle. I mean, go to a library called Hacklestar that uses F-star, but there's many other tools like Fiat. And so for assembly, even there are tools that will allow you to do this. So this is how Hacklestar works, the library that we develop in my team. So on one extreme, we have the standard, which is kind of like the RFC. And on the other extreme, you would like to get out optimized code. So what we do, in fact, is first we transcribe the standard as a specification in F-star. We call this pure F-star. So this purely functional code, no mutable state, okay? This code can use high-level notions like sequences. So you don't have mutable arrays, you have sequences. You have mathematical integers with arbitrary precision. And you also have machine integers with fixed precision. So these are the kinds of objects you can manipulate in your spec, but not much else. Then when you want, for the C code you want to produce, you in fact write it also in F-star, in a sublanguage of F-star called low-star, which has a C-like memory model. So in this low-star language, you're not allowed to use arbitrary precision integers, but you can use machine integers, and you can use buffers, which are mutable arrays. And then once you have written these two versions, one is the high level spec and one is the low level implementation with all the optimizations that you want, then you can prove that they match each other. And for this, you use the F-star type checker and you prove that there is no memory safety problems, no functional correctness bugs, and that the code is secret independent. And once you have verified this, you can compile the F-star code down to C or to WebAssembly or even to OCaml if you like. So this whole framework is built around a verification framework and programming language called F-star. For those of you who know programming languages like OCaml or Haskell, this looks programming in F-star is just like that. But in addition, it's also a verification system. So for those of you who know Coq or Isabelle or these kinds of programming systems, the F-star is both a programming language as well as a verification system of this kind. The main difference is that a lot of the boring proofs in F-star are automated, or they try to automate as much as possible using the Z3 or SMT solver. And although you're programming in a language like OCaml, you can actually compile this out both to OCaml, but also to languages like C and WebAssembly. But different subsets of the language go to different targets. So this makes it an ideal framework for doing both your program development as well as your proofs side by side. And this is under active development. I encourage you to look at it if you have time. All right, so using F-star, we can develop an entire library. So in 2017, there was already this library of a bunch of algorithms that are all implemented and verified in F-star. How fast was it? Well, it's as fast as any handwritten C code, but it was not as fast as assembly code. Why? Because assembly code can use these special instructions like for SIMD vectorization and so on, which it's trickier to do from C code. So this is as fast as existing C code, but not as fast as assembly code. So here, let's take a little pause and say, okay, so what is the state of verified crypto? What are the solved problems? What are the open problems? So today, if you came to me and said, hey, can I download a verified portable C implementation of this algorithm or that algorithm? For many of the standard algorithms, the answer is yes. So it's not just from Hacklestar, but you can go get it from Fiat Crypto, from SAW, from VST, from Jasmine. I mean, you can get a bunch of verified C implementations. But can you be sure that the C compiler preserves the correctness despite the optimizations that the C compiler is going to do? That is an open question. If you use CompCert, you get some guarantees, but you're not guaranteed that the side channel protections in your C code will go all the way down to assembly. There is some active research work in this area. If you're interested, I encourage you to look at this line of work on CT CompCert, for example. So that's for C code. What about verified assembly code? I want super fast assembly code, but which is verified. Can I get it? Yes, because there are these projects like Whale and Jasmine, which will give you verified assembly crypto code for various algorithms. For the most popular ones, but not necessarily for everything that you need. But what if I want a verified implementation of something completely new, like a post-quantum chem or a zero-knowledge proof system or a FHE scheme? This is harder because this is still very much in the level of research. There are not so many implementations of this. You will probably end up doing, this is like a PhD level problem at this point. And can I verify my own implementation if you ask me this? Well, I'm afraid at this stage, the tools that I've described, and there's many, many tools here and many more in the survey paper, require quite a lot of expertise. So it's something that you dedicate several years of your life to, okay? But you can reuse many existing verified components to build your implementation. But if you want to verify by yourself, it still requires quite a lot of PL expertise, I would say at this point. So that's a bit of a negative in terms of usability of these tools, but a lot has already been done. And if you get willing to spend time, you can do a lot too. And then the last question in this zone is, well, okay, you prove correctness for your code, but what about side channels? There's so many side channels out there, right? Timing, power, fault, whatever. And can I prove the absence of these kinds of leaks in my code? For timing, yes, I would consider the problem to be more or less solved. But for almost all the other side channels, this remains an open problem and an exciting problem of research. So if anybody is interested, this is certainly how do you verify the absence of certain kinds of attacks? How do you verify that a countermeasure is preventing, say, a fault attack? This kind of thing is still very much in the hot research. Okay, so that was for the state of the art, but let me show you a little bit about how you can do better. So So I told you that in our libraries that we have like various versions of each algorithm. Can we verify them all rather than just verifying one implementation here, one implementation there, like Jasmine does or Hacklestar does? The answer is yes. The idea is you want to write once the code, verify it once, and then compile it in optimized implementations for each of these platforms. And that's the idea behind this project called HackleXN, with a paper at ACM CCS 2020, where we write generic SIMD parallelizable code. So even when we first write the code, we don't write it scalar. We write it in a way that it can be parallelized. Okay, but then you can instantiate it. One of the instantiations is scalar code, but the other instantiations are vectorized parallelized code. And if you write this from the very beginning with the idea that you might want to parallelize this, then you can write code which is generic, where tomorrow if somebody comes up with AVX 1024, it'll just be a little tune and then it'll spit out the right code for that new platform. And you can verify it once and for all. And then you can specialize and compile to each target architecture. And for this, we use a special technique called verified metaprogramming in F***. I won't really describe it, but if you're interested in it, there's also very interesting PL research to be done on how to compile and verify this kind of code. So for HackleXN, the idea is you first write a scalar spec, which is just a high-level specification of the mathematical function. But then most of your effort is actually in writing this generic vectorized spec, which is a specification as well, but it is implicitly parallelizable. And you prove that this parallel spec is correct. And once you've done that, the next step, which is to implement the parallelized implementation in C, basically, is standard amount of verification work, but not so much. The most of the work is on the left-hand side. And the good news from this is that from this verified implementation, you can then compile out 32-bit code, but you can also compile out SIMD vectorized code for many different platforms. So that really speeds up everything. For example, if you wanted to vectorize something like SHA-2, this is one round of the SHA-2 compression function. So what it means is that you're going to take 8 words and mix them up, and you get 8 more words out, right? But when you say word in SHA-2, we actually mean 2 different things. For SHA-2 256 is 32-bit words. SHA-2 512 is 64-bit words. So first, to specify even the scalar operation on the right, you have to basically write a spec which is very generic, which says, okay, if it is SHA-2 256, you do this. SHA-2 512, you do something else. And you can do this in a high-level language like F* or in something like Coq. And then you can write down your transformations. This is your little shuffling function that you're writing down. But the next thing you're going to do is to write the vectorized spec. And the vectorized spec is going to manipulate 4 SHA-2 states in parallel. The way it's going to do it is going to take your 4 SHA-2 states. It's going to transpose them so that it becomes an array of vectors. Rather than 4 arrays, you have an array of vectors where each vector has 4 elements. Then you apply the transposition to these vectors so that it's happening in parallel on all 4 states. And finally, you untranspose it back to get back the original format, which is the 4 different SHA-2 states. And this is kind of the standard way of doing very naive vectorization, where you're not really using anything clever, you're just doing things in parallel for many different inputs. And if you wanted to specify something like that in F***, what you have to first do is define what the width of your vectors is. You could leave it completely unspecified, but in most common use cases, you're going to have a width 1, which means scalar, or 2, 4, 8, 16, these kinds of things. And once you've defined your widths, you can define your state, which is going to be a vectorized state. On the left is the scalar state, on the right is the vectorized state. And then you define your vectorized operations, which turns out look exactly like your scalar operations. It's just that you're doing them in parallel on all of the elements of the vector. And finally, of course, you have to prove that the thing on the right is consistent, let's say, with the thing on the left, which means if you transpose states on the left to the right-hand side form, apply all the right-hand side operations, and then you transpose back, then it is as if you did the operation on the left on each element of the vector. And this is the standard kind of proof technique, which we have many libraries for, and we can do this uniformly. So in HackleXN, this is what we did. We have many different algorithms that we vectorized to get performance, which now starts getting much better, closer to assembly, hand-optimized assembly code. There is still a small gap, but you can close that even. And you get, from one verified implementation, multiple deployable platform-specific implementations for free. So this closes the gap between high assurance and high performance. You can close the gap even further. If you really need to use assembly for something, then you can verify that as that element of your code using a language like Whale or Jasmine, and then incorporate it back. And that's what is done in this tool called Evercrypt, where you take verified code from Whale, verified code from Hackle, mix them together. And if you mix them together, you can get performance which beats all the implementations out there, for example, for Crypto 5519. Even handwritten or hand-optimized implementations without any verification, verified code can beat the performance of this unverified code. So there is no real need or performance-based need for avoiding verified code anymore. Okay, so we know how to close the gap completely towards any assembly or C implementation for many different crypto primitives. So this code that I've been showing you, HackleStar, is actually in deployment. It's if you're using Firefox, you're using HackleStar or WireGuard or some blockchains, or if you're doing elections with Election Guard, you're using code from HackleStar. So this is a successful cryptographic software. So let's shift a bit for the last part of the talk towards saying, okay, how we go up the stack, right? So if you remember, this was what our target was. I focused on the bottom part of the stack for most of the talk. But how do you verify the things on top? So again, Signal, we said it has a fairly innovative protocol design. In fact, if you look inside it, the first part is called, it's a one-shot authenticated key exchange called X3DH. Then it's got this key ratcheting mechanism, which provides this novel guarantee called post-compromise security. It's got a hash ratcheting mechanism, which provides forward security. And then it's got authenticated encryption scheme, which is fairly standard. What's interesting about this protocol is inherently recursive, because with every message, you can change the keys, and the new keys depend on the previous keys. So if you want to ask about what is the security of message number 20 in a Signal conversation, it depends on the security of the previous key, the previous key, the previous key, all the way back to the X3DH1. So you have to really, even the security guarantees, if you state of a Signal protocol, are inherently a recursive inductive guarantee that you get, where each message builds upon the security of the previous message. So how do we mechanically verify that this protocol is secure? And can you prove that it is correct? Well, you can take the protocol and you can formalize it, right? So the picture on the right more or less represents all of the operations that are happening in the first two messages in Signal. And if you zoom in on it, even for the first message, before sending the first message, Signal does 5 Diffie-Hellman operations. So 4 just to do the initial key, and then 1 more to send the first message. So this is already like a bit more complicated than TLS, in the sense that TLS had only 1 Diffie-Hellman operation. Here we are doing 5 Diffie-Hellman operations, and each of them is for a different purpose. The recipient has 3 Diffie-Hellman public keys. The initiator has 1 long-term Diffie-Hellman public key, and then there are many ephemeral Diffie-Hellman public keys all mixed in. Okay, but you can formalize this in a formal tool. For example, you can write down this protocol in a tool called ProVerif, and then analyze whether this protocol is secure under some highly abstract, symbolic abstractions of cryptography, and try to find attacks against this protocol. You can also formalize this protocol in a tool called CryptoVerif, and then do a game-based proof that this protocol is secure. And these things work, and I encourage you to read that paper. But the issue is that since every message, the security of each message depends on the prior messages, the state that the tools have to maintain keeps growing, which means after 3 messages, typically both of these tools at least blow up. I mean, they cannot handle the 4th message anymore, because the security of the 4th message depends on the 3rd message, depends on the 2nd message, and so on. And it gets the security becomes harder and harder to prove, because these are more or less automated tools. You don't do inductive proofs in this. You want to prove them by exhaustive search. And so there are limitations to what you can prove, but up to the first 3 messages, yes, you can prove all the properties, try to find all the classic attacks on key exchange protocols, and you can do this for this protocol. So let's assume that you have a crypto proof for it, either handwritten or done with one of these tools. Can you prove that the code for Signal is correct? Yes, by using the same kind of thing you were doing for Hackle. You can write the spec, you can and you can prove in F* that the code matches the spec. okay? And then you can take this code and you can plug it back into a signal implementation. And then you get a verified signal implementation in the sense that inside it, all the protocol code has been verified. And this was done in a paper at S&P 2019, where the entire signal implementation was verified and then plugged in back into the signal messenger so that you could just use it as part of your messaging application with no discernible change. In fact, it was even faster than the previous implementation. Of course, the problem here is that we only have a proof for three messages, which is a bit dissatisfying, but we'll see how to improve that. Before doing that, let me kind of also step back for a few minutes and say, okay, so what in the arena of verifying protocols and protocol code, what are the solved problems and what do I consider the open problems? So today, if you have a brand new crypto protocol for IoT or for your blockchain or for whatever, and you want to analyze the security of this and find all kinds of attacks on the logic of the protocol, yes, you can do it. There's many tools, especially ProVerif and Tamarin, where you can code up the protocol and you can run it and it'll find all kinds of attacks against this protocol. Okay, so many realistic threats you can eliminate by just exhaustively searching for them. Of course, if your protocol has this kind of recursion like Signal does, or it has an arbitrary size, like it's a group protocol with unbounded size, then these tools will struggle because they are doing an exhaustive search. But if you don't have that kind of those kinds of generalities, this is a solved problem. What if you want to have a crypto proof, like a game hopping proof or a simulation-based proof or reduction-based proof? Can you build a mechanized proof, machine-checked proof for your crypto protocol? Yes, but it takes much more work. Okay, so there are tools like CryptoVerif, EasyCrypt, CryptHall, and many others, where you can write down mechanized proofs for these protocols in a semi-automated way. Often the user needs to provide lots of input. Often you need to have a lot of experience. The tools that I showed you before, like ProVerif and Tamarin, are more or less push button. You push the button and it will say yes or no. You need expertise, but not as much as for these ones. What about really like new kinds of things that I'm deploying today, like some zero-knowledge proof system, multi-party computation, some kind of group key exchange? Can I prove them to be secure using a machine check proof? Possibly, but this is a hot area of research. So this is like ongoing open problems. I welcome you to kind of indulge yourself in this area if you're interested. What about code? Can I prove that my code is correct, as in it's actually doing what it's supposed to? Yes, there is a whole bunch of software verification tools now for Rust, for C, for F-star, for Haskell that you can use that you can prove that your code is correct. That's no longer, I mean, if you're concerned about your cryptographic code, you should prove that it's correct. Can you bridge the two? Can you build a crypto proof, but directly for code? Yes, there are some research projects that have tried to do this. It's a lot of work, but you can take a look at these projects and you can actually try to do a crypto proof directly on the deployed code. Sometimes it works. Okay, and the last question. Okay, we started off this talk by saying, let's try to verify the signal messenger. Can we do it? No, because it's too big. 30,000 lines of code is not going to be something that any of the tools I've mentioned will scale to. Okay, 30,000 was 10% of Signal, right? But if you are able to rewrite that code in some highly specialized way, which will help your proof, then yes, maybe you can do it. Okay, so let me end the talk by talking about this project, which I'm very excited by. It's joint work with Ralph and many of his students at Stuttgart and Abhishek Bichawat at Gandhinagar, which is called DY-Star, where we're really trying to also do security proofs alongside doing these functional correctness proofs in F-star. Okay, it's a scalable symbolic security proofs for F-star protocol code. And the basic idea is you write the code in F-star, you write the spec in F-star, and then for the spec, you prove security also in F-star. To do this, we have built a layered kind of architecture, but at the bottom, we have a very concrete semantics of the global trace of protocols, where you can really specify what the security guarantees and the attacker threat model is. On top of this, we have a symbolic abstraction of crypto, which is called the symbolic runtime model that we built. And on top of that, we build various proof techniques and abstractions called the labeled security library. But we prove the soundness of these abstractions within the system. And finally, we build protocol models on top of this labeled library. So if you want to model your own protocol in DY-star, you can ignore everything below it, and you get this nice high-level abstract API on top of which you can build your protocol code. Okay, and that's the thing that you will verify, and that is usually very compact, and the verification usually is pretty quick. Okay, and if your protocol code fails to verify, it could mean that there's a potential attack. It might mean that you have to provide some more annotations for the proof to go through. So you're building symbolic proofs in F-star for your code, and this is the same code that you will then run on the network so that you can even compile it to C or open WebAssembly in some future version, so that it's actually an efficient, high-performance implementation, but with security proofs all within the same system. So I don't have too much time, so I'm going to skip the taste. But basically, just to give an idea of the kinds of proofs that you do, when you do something like Signal, if you remember, the first message had 4 Diffie-Hellman operations. So each Diffie-Hellman operation is meant to give you a different security guarantee. And this is captured within DY-star in the notion of secrecy labels. So this is the label of the key that comes out of X3DH, but each of these lines is basically the guarantee given by one of those Diffie-Hellmans. So one of them is a static Diffie-Hellman, one of them is an ephemeral, two of them are ephemeral static Diffie-Hellmans, and each of them we can carefully characterize the fine-grained security guarantees you get from that Diffie-Hellman and combine them all and then use it to prove the security guarantees of Signal. And each of these steps is proved sound within the system. So in using DY-star, we've already verified things like Signal. And this, in fact, is the first mechanized proof of Signal for an arbitrary number of rounds. So we don't have the limitations of ProVerif or CryptoVerif, where we had to limit to 3 messages. We can go for any number of messages. And it's also a proof for an executable implementation of Signal. The verification time in DY-star is linear, which means it's very scalable. So it takes a lot more work to do an individual proof, but it doesn't grow exponentially like many other tools. It grows linearly. However, yes, you need to provide annotations. So you don't have to write the full proof, but it's also not push button. It's somewhere in between the two. You have to write annotations, and sometimes it could be like if you write code of 1,000 lines, you might have to write, I don't know, 500 to 600 lines of annotations, which it's a heavy burden, but much less than many other proof systems. So that's what I'm very excited about this year. We have lots of interesting results and hopefully more results in the coming year. Okay, so to conclude, the various things that we saw. So what is the good news? The good news is that if you want to verify crypto algorithms, crypto protocols, find attacks, for many of the classic designs, for many of the simple analyses, it's actually more or less a solved problem in the sense that there are interesting research still going on here, but there are good foundations on the basis of which you can start and do interesting things with. But there are other things which are more very researchy, maturing, active research, such as zero-knowledge proofs, MPC, FHE, how to verify hand-optimized assembly code. This is still, I would say, a little bit on the edge of being solved, but I would not call them solved in any way. And there are many, many problems that are really open. In particular, how to prove the absence of various kinds of side channel attacks that have been known for a while. We still don't know how to do that. And of course, all the code that I've shown you, all the tools that are working here are working on code more or less that people have written for the purpose of verification, as in we were willing to change the code in order to verify it quickly. But often, of course, we want to verify code that has been written by non-verification experts, which security developers, and how to kind of interface between security developers who are writing real code and these verification tools remains an interesting and open challenge and quite unsolved. So if you're interested in this topic, before I leave the two questions, I'm going to encourage you to show you 2 links. One is the Indocrypt workshop, which we are holding every year, hopefully, in India in December. Last year, it was co-located with Indocrypt. This year, it's co-located with FST-TCS. Unfortunately, registration is already closed for this year, but you can attend next year. Look at that website. And there are many open internships, PhDs, and postdoc positions in this zone. Please communicate with me if you're interested. There are job offers in India, but also I know of job offers at Stuttgart and Microsoft Research. So there's lots of interesting research to be done. I'm a little bit over time, but I'm going to stop now.
So thank you very much, Karthik, for this very inspiring and nice talk. So we have time for questions. Are there questions? I see there's something already in the chat. So let me read out the first one. What are the present challenges if you want to verify any implementation in JavaScript, or we want to verify whole large code written in JavaScript, rather only small code written in C?
Thank you for that question. JavaScript is, okay, if you write your code directly in JavaScript and then you want to verify it, it's traditionally considered a very hard problem because of the semantics of JavaScript is particularly naughty, especially if you use all the features of JavaScript. But there are many approaches which work well here. So among the things that I showed you, all of the code that we verify in F*, you can compile to C, but you can also compile them to WebAssembly, and WebAssembly with a JavaScript wrapper around it. So you can use it. WebAssembly is, in fact, now in most JavaScript frameworks, you can execute WebAssembly within JavaScript. So that's, if you want to use the tools I talked about and actually take the verified code and put it into JavaScript, it's already done. You can do it right now. If you want to write your code in JavaScript and verify it, you'll have to follow very strict discipline. So there is various proposals that people have made, including SES, including defensive JavaScript, and many other subsets of JavaScript. If you write your code in those subsets of JavaScript, then yes, we can apply some of these verification tools to them. But if you're going to take a general purpose JavaScript app of, I don't know, 30,000 lines, I would say it's hopeless to verify.
Okay, thank you. We have another question. Do you feel cryptographers need to create simpler schemes without compromising security, or is security the only priority and programmers need to be careful?
This is an interesting question, and I think people are really wrestling with this already in the NIST post-quantum competition, where there are some schemes which seem to be harder to implement securely than others. And this has become a bone of contention as to whether this should be a disqualifying feature. You know, you might have a super secure scheme, but maybe it's hard to implement correctly. So I would say that indeed, it is the responsibility of a cryptographic designer to write their own implementation at least once and show how this can be done securely. And if you have to jump through many hoops to implement your scheme securely, then it's just irresponsible to put it out there, I would say. So that's what I feel. But you know, I'm not designing crypto schemes, so maybe I'm biased from the other side.
Okay, so let me ask one more question from the chat, and then we go to the floor and ask there. So, so this is an interesting question about documentation. So, how far can one go in terms of protocol verification when the protocols are described in English only, and that also is purely documented? For example, Intel SGX.
Yes, I don't want to indulge in SGX bashing here, but I understand the pain that the questioner is expressing here. I agree that there is a problem in terms of there is always going to be a gap. I mean, I kind of jumped over it in some sense, saying, oh, from the RFC, you can go to a spec very easily. It might be true for certain kinds of crypto specs where it's basically a mathematical function being described in words and pseudocode. Maybe writing a formal spec is not so hard, but a lot of specifications are not like this, especially protocol specifications. So recently, Ralph and his students and in collaboration with me, we built a model of the Acme protocol, which is hundreds of pages, or at least almost 100 pages of text. And it's not trivial to kind of figure out whether or not you're correctly modeling and formalizing this kind of protocol. So one solution I see coming forward is to try to develop specification languages that authors of specifications can use and embed within their spec. But these specification languages are far formal with a formal semantics. So one of the languages we're developing in my team is called HackSpec, and it's getting a little bit of traction. And the idea behind HackSpec is indeed to write formal specifications of crypto primitives and maybe some parts of protocols in a way that is executable, in a way that can be translated to F-star, to Cork, to EasyCrypt, and these kinds of things. But is also very succinct and readable. So something that you can put in place of pseudocode, let's say, within your spec. That's, again, much easier to do for things like crypto primitives, but maybe much harder to do for things like protocols. And even much harder to do for things like APIs like SGX, because there you have to really wrestle with a lot more constraints and a much larger committees of users and developers than the ones that I'm speaking of. But this is a valid and, as far as I know, unsolved question.
Okay, so let me give the people at the venue a chance to ask questions. Do we have questions there?
Thank you, Professor Bhargavan, for your wonderful talk on high-performance cryptographic softwares with high assurance. So here, many of the participants are at the venue, and they would like to ask a few questions, couple of questions there. So, dear participant, anyone is having any questions? Then.
So, my question is this: that JavaScript is widely used because of its language feature richness. And the moment you go for the verification, you have to reduce those features. So can we see in near future when we can use full feature rich JavaScript with formal verification like we have in hardware industry?
I suspect that full JavaScript is hopeless. I think JavaScript in strict mode, maybe, which is actually still quite expressive. Huh? I mean, a lot of the problematic features of JavaScript for verification are features that most people never use. Okay, it is just that it is something that we have to be aware of because the attacker might use it. So if I want to make a little, the problem with JavaScript is that if I want to make a little component which I verified and I put it inside a much larger JavaScript implementation, the outside JavaScript implementation can redefine the prototypes in a way that all my crypto on the inside and my secret keys on the inside are completely leaked to the environment. So if I put it on a page where there is some malicious JavaScript on the outside, I can give you no guarantees about it. With WebAssembly, we can give a few more guarantees, but again, not very strong guarantees in the current setting. If you promise that your entire web page is using strict JavaScript, we can give you some more guarantees. So JavaScript is a hard target because it was designed to really allow anybody to change any behavior of any object, and so that's particularly hard. Okay.
So
if you use subsets like I don't know, the Facebook subset or React, I don't know, or TypeScript, then again you might get some good guarantees. But overall JavaScript is hard. But most people in the field now are focusing on Rust, because with Rust we think that even giving all the features of Rust, we can still give you good guarantees. But JavaScript, not so sure.
Okay, so that means as we are heading toward more JavaScript in web application and other places, so that means we are heading toward more insecurity. Yes,
unless you self-impose some limitations on the code that you will deploy. And there are ways of doing this. If you're talking about scenarios where you have isolation features like frames, you can say, okay, I'm going to guarantee that everything within this frame is secure and it's only communicating with the other frames in a certain particular way. But if you're going to drop all of your code in a sea of JavaScript within a single origin, I cannot give you any guarantees in this day.
Yes. Thank you.
Any of these participants? Anyone would like to ask any question?
Okay. Otherwise, I also have another question in the chat. I could ask that one, and probably the final question, because then we are running out of time. It's a general question about like usability. So how can math students with zero knowledge of computer science can learn or build these types of program implementations? And so how is it like it's essentially what you said on your last slide, like how can we like give non-experts ability to do some kind of verification?
No, it's a good question. And it's not hopeless. I mean, I'm quite positive about the answer to this, because it depends on what kind of implementations you're thinking. Okay, so if you are a math student, let's say, and you have a new scheme for doing some kind of homomorphic encryption using some kind of field arithmetic, and you want an implementation of it, it is possible for you to write your scheme fairly nicely, fairly mathematical form in, say, Coq, and then use the fiat crypto framework to automatically compile it to C. So you don't need to know the low-level details of C or computer science. You write your thing in these high-level mathematical descriptions and it gets compiled. Okay. There are some other proposals like this where you can write mathematically oriented, let's say, algorithms, and then it gets compiled to provably correct low-level code, which is very efficient. So you don't actually ever have to write that. So that's one plus for you. The negative is that almost always for new schemes these days, performance is a big constraint. I mean, it's the reason a lot of the very nice cryptography we've had already for 15, 20 years was never deployed widely was because they were never performant enough. And now maybe they will get deployed. Even elliptic curve Diffie-Hellman was the first time when people wanted to then deploy Diffie-Hellman everywhere, which means that if performance ends up being a big concern, you will have to learn some computer science in order to optimize the code. Otherwise, it just will not, nobody will use it. So you can get started very quickly, I would say, using verified libraries for which are already available, or these kinds of compilers, which will allow you to write your thing in a very intuitive way and then compile it down. But that's just the first version. The first version you can do very quickly. But then you probably should communicate with some computer science students and get them to improve your implementation after that.
Okay, so some advertisement for computer science. Very good. So with this, thank you very much, Karthik, for this exciting talk. And well, hope to see you soon. Thank you very much.
Thank you so much, guys. Thank you. This was a great pleasure and honor.
Thanks for being here.
Thank you, Professor Bhargavan, for such a nice and interesting talk. And we are really enriched by your discussion today. And thank you, Professor Ralph and Professor Kaur, for chairing this session. The next session will start at 3:45. But before we go for the next session, I have small announcement. As our chief guest, Professor Bimal Roy, is leaving, so for him we have a small token of appreciation from the whole organizing committee. So I would request Dr. Kaur to give Professor Bimal Roy to a token of appreciation. Thank you.
But is my voice okay? I'm from a distance from the mic.
Good afternoon once again and welcome back to today's first paper presentation session. This session focuses on public key encryption and protocols. For this session, we have the two session chairs with us, Professor Sharman S.M. Chow and Professor Rana Barua. So over to you, to the session chair. Thank you.
Hi. Sharman, you please take over because most of the presentations are online.
Oh, okay, thanks. I will do that. So we have very interesting talk today, and we will start with something about ID-based matchmaking encryption, and the talk will be given by Lugi, if I pronounce your name correctly. So I would like him to introduce his co-author. So the floor is yours. Thank you.
Hi everyone, my name is Luigi Russo, and today I'm going to present you this paper entitled Identity-Based Matchmaking Encryption Without Random Oracles. This paper has been written with Danilo Francati at Aarhus University, Alessio Guidi and Daniele Venturi of Sapienza University of Rome. Sorry.
Luigi, sorry to interrupt. Can we have your video on, please?
Yeah, sorry. Can you see me?
Yes.
Yes, thank you.
Yeah, sorry. Okay, so before going to details of the paper, I will start with a brief introduction about the topic. Identity-based encryption is a type of public key encryption introduced by Adi Shamir in 1984. In this context, users do not require public keys, but the public keys are just some identifying information, for example, email addresses. So in this figure, we can see that Alice, in a classical scenario, wants to send a message to Bob. She doesn't have to retrieve his public key, but can just use his email address as public key. IBE is a powerful primitive that has been widely studied, and there are a lot of applications. Among them, I just recall some of them. For example, the revocation of public keys, the delegation of decryption keys, the authentication, and many, many more. Among the flavors of IBE, a very important one is the so-called anonymous identity-based encryption. In particular, this captures the following scenario. Given a ciphertext, no adversary should be able to distinguish the target identity from a random one. So, for example, Alice encrypts a message to Bob, and no adversary should be able to understand that the ciphertext is really directed to Bob rather than, say, Charlie, so another user in the system. Identity-based matchmaking encryption instead is a novel primitive introduced at Crypto 19 by Ateniese, Francati, Nunez, and Venturi. In this context, we have that the two parties, so both the sender and the receiver, can specify a target identity. So the sender can specify the receiver identity, as in the normal case, but also the receiver can specify the sender identity. So when both target identities match, so we say that a match occurs, the decryption is successful, so the receiver can retrieve the plain text. Otherwise, we want that no information has to be leaked. In particular, the sender's identity, the target identity, and the plain text have to remain hidden. Identity-based matchmaking encryption is a special case of matchmaking encryption, which allows parties to send messages specifying arbitrary policies. So this is the syntax. We have a setup algorithm that generates the master keys, the master public and the master secret one. We have three algorithms for the keys. The sender key gen that takes in input the attributes of the sender and generates the keys associated with these attributes. We have the RKGen that does the same, but for the receiver side. And we have this PolGen algorithm that takes in input an arbitrary function, an arbitrary policy phi, and generates a key associated with this policy. We then have the two classical algorithms, encrypt and decrypt, where the encryption algorithm takes in input an encryption key associated with the attributes of the sender, a general policy R that must be satisfied at the receiver side, and the plaintext. And finally, we have the decrypt algorithm that takes in input the decryption key associated with the attributes of the receiver, a decryption key generated with the PolGen algorithm associated with a policy S that the sender has to satisfy, and finally the ciphertext. In the identity-based context, instead, the encryption and decryption algorithm takes in input directly the identities, so the target identity rho and the target identity sigma. So there is no need to implement this PolGen algorithm, because otherwise the performance would degrade, in the sense that we would have too many, basically one key for each sender, and so this is not acceptable anymore. Also, identity-based matchmaking encryption has a lot of applications. In particular, it finds applications in all those settings where an IBE with strong anonymity guarantees are required. For example, the authors of the original paper have implemented a privacy-preserving bulletin board over Tor, using Tor hidden services. And this can be used, say, by newspapers to collect information from anonymous sources. So anyone can encrypt a message, can specify a policy, can publish it on the bulletin board, and anyone can try to decrypt, specifying clearly a standard policy. So we now move to the main contributions of this paper. And there are two main results that we have achieved. The first one is that we have given a stronger and more meaningful security definitions in the context of IBME compared to the original paper. And the second one is that we have constructed the first IBM scheme without random oracles. So we have to define what is privacy in this context. So privacy, as defined in the original paper, is defined through an indistinguishability game, where an adversary has to commit to two messages, two target receiver identities, two sender identities, and then the challenger samples at random a bit B and generates samples a key associated with the attributes sigma B, and gives the adversary a ciphertext that is just an encryption of the plaintext MB. Then the adversary has to tell apart the two experiments. The problem is that this privacy game offers no guarantee when the receiver's identity matches the target identity specified by the sender, because we somehow have to restrict the class of the adversaries. So we define a class of valid adversaries. And the problem is that since the receiver can choose sender's identities on the fly during the decryption process, the authors of Crypto 19 paper have not considered adversaries who do not hold a decryption key for the target identities. And this, for example, implies that we can build some very strange schemes, for example, the following one, that satisfy the privacy, the privacy as defined by them. So take any anonymous IB scheme, encrypt as a plaintext the plaintext concatenated with the sender attributes, and then what the receiver can do is just to decrypt and see if a match occurs between his policy and the sigma. But then he is always able to retrieve the plaintext and sigma, so this somehow breaks the security, even though the security seems to be guaranteed. So how is that being defined? So this suggested us to move to upgrade the privacy definition to the so-called enhanced privacy. In this context, the sender's identities remain hidden even when the adversary holds a decryption key for the target identity. So we have redefined the game, we have modified it. Now the adversary has to commit to sender distributions, these are ID 0 and ID 1, rather than to sender's identities. And now we allow the challenger to sample from this distribution. So we allow an adversary to hold the decryption key for a target identity, but there is a constraint that these distributions have to have some high mean entropy. So the previous scheme, the contrib one, is not secure anymore under this enhanced privacy property, because we can just use an adversary that samples two ID0 and ID1 with a high mean entropy, but whose intersection is empty. So once, if it owns a decryption key for the target identity, it retrieves the sigma attributes, and then it's easy to distinguish the two experiments. I briefly introduce what is a reusable computational extractor, because this is used in our construction. Computational extractor is a polynomial time algorithm that takes in input a public random seed S, a value X that has to be sampled from a distribution with high mean entropy, and it outputs a value Y that is pseudo-random. A reusable computational extractor is a computational extractor that can be safely evaluated multiple times on the same input. And we used it in our construction that is built on top of the anonymous IBE of Gentry, 2006. So we start from this anonymous IBE scheme. We add a second layer of encryption using a sort of one-time pad. And the randomness of this one-time pad is derived via a randomness extractor, where we publicly we publish the seed X. This is attached to the ciphertext, and we extract using this seed from the sigma, that is the attribute, the sender identity specified at the decryption time. This construction achieves our stronger notion of security, which, by the way, implies the previous one. So this is private. And so very briefly, how the decryption works. The first layer of encryption is removed, and this is done relying on the anonymous ID of Gentry, and then you just remove the second layer of encryption if you make the right guess for the sigma. And that's all. So thank you for your attention. Here there is just a brief list of references that I've used in the slides.
Thank you.
Yeah, thank you.
Thank you.
Are there any questions from the audience? Yeah? Yeah, okay. I have a query. Instead of, have you ever thought of attribute-based matchmaking encryption? Because you talk about policy. So instead of identity-based matchmaking encryption, have you thought of attribute-based encryption?
Not in this paper, but in the Crypto 19 paper, matchmaking encryption for arbitrary policies, for arbitrary users, I would say, is also managed, is also handled. So in the matchmaking encryption captures is a generalization of attribute-based encryption. So, but in this paper, we didn't address the general case.
Okay. So any online question, Sherman?
Maybe I ask a follow-up. So first of all, I apologize for pronouncing your name back. And so I understand from that crypto paper, it's still used relatively heavily primitive, right? So yeah, maybe your trade secret, but have you started to thought of how to do a weaker version of policy, but using weaker primitive? Anything you want to share?
Sorry, I didn't.
Basically means without using functional encryption, have you thought of how do you still achieve some meaningful policy beyond equality?
You mean for arbitrary policies?
Yeah. But not all the way arbitrary, but maybe some weakened one, but somehow you can manage to use such pair maybe.
Okay, so for arbitrary policies, clearly we use the functional encryption, or well, randomized functional encryption. So it's even a stronger notion of functional encryption, because the authors have proved that this functional encryption somehow seems to not be sufficient to construct matchmaking encryption for arbitrary policies, because there are two policies that have to be matched at the same time. Okay. We have considered the easiest case, we can say, that is the equality policy. So identity-based matchmaking encryption is just considering the equality policy. For the intermediate case, we didn't address that, but it would be interesting, I think, to see what we can achieve. Yeah.
Yeah, I think so. Thank you. I'm also very interested. Sorry, we essentially used up the time, but we do have another Q&A room after the talk, right? So yeah, please stay tuned and just let us know if you have further questions. Hope to see you in the Q&A room. Otherwise, thank you.
Thank you.
Yes.
Okay, thank you so much. And we will have the second paper also about public key encryption, but about something also different, how to achieve voice security without key update. Okay, and we have Shanya Lutasan, who will present their work. So the floor is yours.
Okay, thank you for the introduction. I'm Seiya Nuta, and I will talk about false key public key encryption without key update from proof of stake blockchain. This is a joint work with Jakob Schult and Takashi Nishide. So here is an overview of my talk. First, false security is a security notion that guarantees even if an adversary gets a secret key, they cannot decrypt past ciphertext using the secret key. And in prior works, in non-interactive setting like public key encryption, false security has been achieved by updating the secret key. So our contribution is to present the first construction of a false secure PKE without key update, assuming proof of stake based blockchain access. And using blockchain in PKEs is unusual, but it gives us some interesting properties in addition to false security. I will talk about interesting properties at the end of my talk. So its core idea is to make our ciphertext decryptable only once by using proof of stake based blockchain as an immutable bulletin board to determine if a ciphertext has already been decrypted. So first, I will talk about background. So in public key encryption, the sender Bob encrypts a message using the receiver I's public key, and then receiver I's decrypts the ciphertext using her secret key. And even if an adversary gets a ciphertext, they cannot learn anything about the message. But it is quite clear that if Eve gets the secret key, they can easily decrypt the ciphertext. So in false secure PKE, we add a new algorithm called update. So in false secure PKE, ICE periodically updates her secret key using the previous secret key. And even if an adversary Eve gets the current secret key, she cannot decrypt past ciphertext because she don't have a previous secret keys, and because they are updated and dated in past. So in a non-interactive setting like a PK scheme, false security has been achieved by key updates, like in a non-interactive key exchange, zero RTT key exchange, and punctuable encryption, for example. So question here is it possible to achieve false security without key update? And achieving false security without key updates provides some good benefits. For example, in our construction, the size of the secret key become constant, while in prior works, they are depend on number of key updates. So in our paper, we present the first construction of a first secure PKE without key update. And the idea is to make a ciphertext decryptable only once using blockchain. So next, I'll talk about some building blocks for our construction. First one is witness encryption. Witness encryption uses NP language, and instead of using key pair like public key encryption, in witness encryption, we use NP statement to encrypt a message and the corresponding witness to decrypt a ciphertext. So in witness encryption, we don't have key generation algorithms, and instead it takes X NP statement to encrypt a message, and to decrypt the ciphertext, it takes corresponding witness to ZX. So next building block is a blockchain protocol. A blockchain protocol is a protocol which aims to maintain a chain of blocks, and it introduces consensus algorithm like proof of work and proof of stake to maintain the chain of blocks without trusted third party. Here I give you abstracted model of blockchain protocol from Goyal and Goyal's paper. In this abstracted model, we have three algorithms. The first one is update state, which communicate with the blockchain network to keep the local machine synchronized. The second algorithm, get records, output the blocks in the blockchain. And lastly, broadcast algorithm takes a message and it writes the message into the blockchain. So one of consensus algorithm in blockchain called proof of stake. In that consensus algorithm, we can assume a following fact. If we assume that adversary has only a few stakes compared to all other honest parties, we can say that adversary cannot create a sufficiently long fork of honest blockchain, because at first in the adversary's fork, they can use their own stake to prove their stakes, but eventually they need to forge or generate valid stake, even if despite they don't have sufficient stake to prove the last block. And in Goyal's paper, they showed that on some proof of stake based blockchain protocols, assuming that adversary have only limited fraction of stake, an honestly created sufficiently long blockchain is distinguishable from adversary's fork. And this property called distinguishable forking property is used in our construction. So next I talk about construction. So a forward secure public key encryption scheme without key update, which is our construction, is consisted by following three algorithms: key generation, encryption, and decryption. And as you can see, it is looks like a usual PK scheme, because we no longer have to add some additional algorithm like key update. So And in our construction, the core idea is to allow decrypting a ciphertext only once by checking decryption attempts in the blockchain. So this means that if adversary Eve obtains the Alice's secret key, it cannot decrypt a past ciphertext because they are already decrypted by Alice, and the decryption are recorded on the blockchain, and thus it achieves the full security. So here is how to implement the one-time decryption. In our construction, we require the first decryption attempt to decrypt a message, a ciphertext. So in this diagram, first Alice received ciphertext and decrypts using the decryption algorithm. And after that, if Eve gets the same secret key, but she cannot use the secret key to decrypt a ciphertext because it is already decrypted by Alice and it's recorded on blockchain. And to decrypt the ciphertext, Eve needs to fork blockchain from before the Alice's record, and creating a sufficiently long blockchain is hard because of distinguishable forking property, which I described before. So let's look into each algorithm. First key generation algorithm is pretty simple because it just generates digital signature schemes key pair and output as they are. So next, in encryption algorithm, first we download the latest blocks from the blockchain, generate a unique message ID, and encrypt using witness encryption. And NP relation used in our construction will be described later. Lastly, the decryption algorithm is a bit complicated. So first, what we do is create an ephemeral secret. And then we sign the ephemeral secret using the long-term secret key and write the signature into the blockchain. After that, we need to wait for a while until the blockchain sufficient grows to satisfy the distinguishable forking property. And then we download the latest blocks from the blockchain. So lastly, we give the latest blockchain and ephemeral secret to decryption algorithm. And then we delete ephemeral secret because it is necessary to prevent adversary to use the ephemeral secret after, and then output the decrypted message. So here is NP relation used in our construction. Because it's a bit complicated, so I will give you an overview of the relationship. So in the relation, we check three facts. First, the ciphertext has not yet been decrypted. So so we ensure that the decryption is the first one. Next, decryptor knows that the ephemeral secret ESK, so that even if adversary gets the secret key and tries to decrypt the message, she cannot decrypt the past ciphertext because she don't know about the ephemeral secret. And lastly, we check that the given blockchain is not generated by adversary, and we can check it using thanks to distinguishable forking property presented by Goyer and Goyer. And the detail of the construction can be found in our paper. So next is discussion. So in addition to for security, our construction has some interesting properties. First is constant key size, because we use digital signature schemes and key pair as our construction's key pair. The size is constant despite previous works depend on the number of key updates. And next one is key leakage detection. Because adversary need to post a valid record into the honest blockchain. So ICE can monitor the blockchain, and if she detect valid record for her secret key, it is a sign of key leakage. And finally, lastly, post-compromise security, because even adversary get the secret key, she needed to decrypt ciphertext before Alice does. So adversary needed to keep decrypting actively. So here is open problems of our construction. First is efficiency, because our construction requires blockchain access, and we use a complicated relation in witness encryption. So this is why our work is still in feasibility result, and it's not yet practical. And another problem is privacy concern. We can notice key leakage, but since ICE need to post a record into the blockchain, anyone monitoring the blockchain will be able to tell when ICE decrypts a ciphertext. So it's like a privacy concern. So here is my overview of my presentation. Thank you.
Okay, are there any questions offline? Any? Okay, then. Okay, I just have a curiosity. You said that the ciphertext can be decrypted only once, right? Isn't that a very strong condition, restriction?
Yes. Because in ordinary public key encryption, we can decrypt a ciphertext many times, but in our scheme, we can decrypt it only once.
Only once. So that seems to be a. You try to remove this restriction, no?
Yeah, but if I allow decrypting several times, it breaks for security, because if the ciphertext can be decrypted many times, it means that secret key can be used to decrypt past ciphertext.
Okay, thank you. Yeah, Sharmin.
Thank you. I didn't see any question yet. David, just feel free to unmute yourself if you want to ask a question. Maybe we want to ask one interesting work, new idea. And so I'm also wondering if there's maybe a random question. So there's another notion called punchable encryption, which also try to address this kind of situation, but maybe by updating the ciphertext. So can it be helpful? Can this kind of technique you propose may be helpful to propose something new about another notion?
Sorry, I couldn't catch that.
Oh, okay. I'm wondering there is another notion called punchable encryption.
Yeah.
Which update the ciphertext, if I understood correctly.
No, it updates secret key.
Both. It puncture part of the secret key. So that's also about key update. So I'm wondering if there can be any implication of your technique to this part.
So you mean there are any relationship with puncturable encryption and between that and our construction, right?
Yeah.
In our construction, we don't use puncturable encryption, obviously, and the difference is that in our scheme, we don't use key updates to achieve for security, and the same thing with puncturable encryption is that their puncturable encryption and our construction both implement fine-grained for security. So after decrypting a ciphertext and after updating the key, the past ciphertext become immediately undecryptable using the new updated key.
Thank you. Yeah, I understand the relationship may be too far away. It's a far-fetched question. Thank you. Any questions from the audience? We do have time. Let me double check whether we have Q&A waiting.
Okay, so let us thank
I guess
the
so.
speaker again.
Yeah, thank you so much. We always have the Q&A session later. Okay, thank you.
Thank you.
Okay, and we now have the last one. So that's a bit different. Is in a tab paper, we try to analyze an existing privacy preserving wide-hailing surface called Trace protocol. And we have the speaker, Pat, if I pronounce your name correctly. So yeah, the floor is yours. Thank you.
Yeah, thank you for the introduction. So this is a joint work with Dr. Srinivas Vivek. In this work, we propose an attack against the ride-hailing service Trace, and mainly we focus on the privacy claims made therein. So first, let us look at some examples of ride-hailing services. In recent years, to give you some statistics, Uber trips have increased from 140 million in 2016 to 6.9 billion in 2020. And so these services are becoming increasingly popular day by day. And the main features of this service are that they provide ride requests at the simple touch of a button. They also provide other features such as fare estimation and reputation ratings, including automatic payments. However, there are several privacy issues when it comes to ride-hailing services. They collect vast amount of information about riders and drivers. In particular, they keep track of pickup and drop locations, time of travel, etc. And there have been several news reports which indicate these violations of privacy. For example, Lyft was sued for violating the California privacy law. Uber employees used their app to spy on politicians and celebrities. Uber were tracking its drivers and they threatened to fire anyone who were attending taxi protests. So there have been several lines of works whose focus is particularly to ensure privacy in ride-hailing services. So Trace is one such protocol. It was a privacy-preserving solution proposed by Wang et al. At IEEE Transactions on Vehicular Technology 2018. The main contribution of this paper is that they hide the locations and identities of riders and drivers from the service provider during ride matching. In addition to this, they ensure efficient and accurate ride matching for riders and drivers in a region. So the three main entities in any ride-hailing service are the ride-hailing server who provides the service, the customers or the riders, and the vehicles or the drivers. So now I'll give a brief overview of Trace. So at the start, the server divides the two-dimensional space into several quadrants. So if you see this figure, N1 is the primary quadrant and it is divided into sub-quadrants N2, N3, N4, N5. N4 is further divided into N6 up to N9. And this is stored in the form of a secret quadtree N. Each quadrant is characterized by the 4 vertices that surround it. So the server computes the masked quadtree En of this data structure and sends it to the riders and drivers. RCs and RVs use this encrypted quadtree to mask their secret coordinates and they send it back to the server. Now the server who has the masked coordinates of riders and drivers finds the list of drivers who are in the same quadrant as RC. So this is done to ensure load balancing on the server and to minimize the number of requests that the server receives. So with this list of drivers who are in the same quadrant as the rider, the server computes the Euclidean distance between the rider and the drivers in that region and appropriately chooses the closest driver. And in this way, efficient and accurate right matching is also ensured. So the masking that is used in this process is through random secret integers, modulo public primes, and all these masked values are exchanged between entities using a public key encryption scheme. So our contribution is that Trace makes the following claims. So given the masked quad tree from the server, the riders and drivers do not learn anything about the underlying quad tree N. And the second claim is that the server can only learn the quadrants in which the riders and drivers lie and nothing more about their exact locations. So we propose efficient attacks. So first attack shows that the riders and drivers can indeed obtain the secret quad tree N that is maintained by the server. And this quad tree represents a spatial division of the region and may leak statistics about the distribution of driver density. To give you more context, smaller quadrants are chosen where the density of drivers is high to ensure minimal load on the server. The second attack shows that the server can recover the exact locations of all RCs and RVs in the region, and this is a clear breach of privacy. We also provide public implementation of these attacks for the security parameters that are recommended in TRACE, and we show a very high success probability of recovery. So to give you a brief overview of our attacks, in the TRACE protocol, when masking is done for different messages, the protocol uses common randomness across different messages. And the reason they do this is so that the arithmetic is correct and that the Euclidean distance and the closest drivers are computed correctly. For example, when the server receives the masked information of locations from riders and drivers, there are several expressions where these common randomness are cancelled and the drivers within the quadrant of the rider are obtained. And so we make use of this common randomness, and we observe that they can be eliminated if we consider different messages that are sent by entities. Subsequently, when these unknown common randomness are eliminated, we are left with a system of linear modular equations only in the unknown plaintext locations. And the plaintext in case of the first attack is the quad tree N that is maintained by the server. In case of second attack, these plaintext are the locations of riders and drivers, which the server intends to know. More importantly, our attack is efficient and it runs in time quadratic in the security parameters. And it is also purely algebraic in the sense that we make no assumptions about the geometry of the two-dimensional space. So the first attack is where the riders and drivers recover the secret quad tree maintained by the server. So we know that they receive a masked quad tree En, and if the quad tree has M nodes, N1 to Ni, the riders and drivers receive the masked quadrants En1 up to Enm. So each quadrant is composed of 4 vertices. Let's say the jth coordinate of the ith quadrant is denoted by Enij. The server computes 6 masked values as shown in the first 6 equations. In these, S and AJH are known only to the server, and Xnij and Ynij denote the quadrant, the jth vertex of the ith quadrant. And with these equations, the first step is that the riders and drivers eliminate the unknown randomness AJH, and this can be done by subtracting every pair of equations. Now, S is also unknown to the riders and drivers, and these also can be eliminated in many ways. One such example is shown in the last 3 equations. So finally, since the riders and drivers know all the Enijh masked values, they are left with a linear equation modulo P, where the only unknowns are Xnij and Ynij, which are the underlying coordinates of the quadrant, or the masked tree, or the quad tree N. So in this way, in this example, we consider 2 quadrants, En1 and En2. And so if you consider them, we obtain a system of 28 linear equations in just 16 variables. And 16 variables because we have 2 quadrants with 4 vertices each, and each vertex is characterized by an XY pair. So, however, we experimentally observed that the rank of such a system was 13, and therefore we couldn't obtain unique solutions. This was simply resolved by considering simultaneous equations for 4 quadrants at a time, En1 up to En4. In this case, we obtained a system of 168 equations and 32 unknowns, and the rank of the system was also 32. And we used Gaussian elimination to obtain the unique values of the coordinates of quad tree n modulo p. So the second attack is where the server recovers the locations of riders and drivers, and this is a more impactful attack compared to the prior one, since this violates the privacy of rider and driver locations. So when the riders and drivers are given the masked quad tree En, they use it to mask their own locations. So suppose XV and YV are the locations of a rider. They mask it with respect to En as shown in these equations. So Rij is a random value integer that is chosen by the rider and unknown to the server. And alpha is a public value. And for each vertex, j equals 1 up to 4, the rider computes Aij. And to mask the order of vertices, the rider chooses a random secret permutation pi and permutes the Aij values and finally outputs A. AI is sent to the server. However, notice that this permutation is over 4 elements, and therefore the server can make guesses row. So if you permute AI and get a candidate AI dash, which is permuted according to row, assume for now that by chance the server ended up on the correct permutation, that is row is pi inverse. So this means that AI1 dash is the same as AI1, AI2 dash is same as AI2, which was originally computed by the rider. And here the server does not know Rij, and that can be easily eliminated from these two equations. And the server obtains a linear equation in XV and YV. So this can be done for j equals 1 to 4, and this means that the server obtains 4 linear equations in the two unknowns XV and YV. And the server solves these equations, and if the system is consistent, then with high probability the server can conclude that rho is pi inverse, and that XV YV that is obtained is indeed the exact location of RC and RV. And we said that the quad tree is composed of several nodes, and so the success probability of our attack can be exponentially increased by obtaining XV YV for each I and finding the common intersection of these solutions. And with high probability, we indeed observed that the XV YV corresponded to the actual location of the riders or drivers. So we provide experimental evaluation of our attacks for the security parameters that are recommended in trace. So the first table shows the average time taken for the first attack where the riders and drivers recover the secret quad tree maintained by the server. We choose different sizes of quad trees from 50 to 100. And we also conduct experiments for higher security parameters than what is recommended in trace. And we observed that these attacks are indeed feasible. The second table shows the attack, the timings for the attack where the server recovers exact locations of riders and drivers. And even in this case, the attack is very much feasible in practice. So in the recent years, there have been several works in the area of privacy preserving ride hailing services. While we saw that trace uses random masking, there are other works, for example, ORide, which uses homomorphic encryption, or PRide, which uses garbled circuits. But our attack is very much specific to trace because it uses random masking, and we use a system of linear equations to obtain the unknowns. However, it is not clear how our attack can be prevented. More importantly, the second attack where the server recovers the exact locations of RCs and RVs, we are not yet sure how to prevent it. However, the first attack where the servers recover the exact quad tree maintained by the server, this can be thwarted by carefully modifying the trace protocol, and the privacy claims for this countermeasure can be proved by using arguments similar to one-time pad. And I would recommend to see our paper for more details. But for future work, it would be interesting to see how a countermeasure can be proposed for the second attack in our paper. Thank you.
Any question from the audience? No. Any question online? I don't see. You are not audible, Sherman.
Yeah, thank you. Sorry about that. Maybe I start with one question. So thanks for the talk. And you mentioned about trying to fix the scheme, but if I understood correctly, if that's about solving linear system of equation, then you cannot really fix it, right? I mean, it's inherently you can invert the matrix if I understood correctly.
So our attack relies on solving a system of equations. You are correct. But it also relies on the fact that there are common randomness used when masking different equations. So when computing the different E and Ij values, the 6 values for each vertex in the secret quadtree, there is common randomness used across, and this is done to ensure correctness of the protocol, where in a later point of time, these randomness get cancelled out and the server obtains the correct expression. If you decide to not use common randomness and use a unique randomness each time, this violates the correctness of the trace protocol and affects the right matching accuracy. So it is not clear how you can ensure correctness of the protocol while at the same time ensuring privacy as well.
Yeah, exactly. So if you just use different randomness, then you can really compute things unless you upgrade to HU, I suppose. And unless you use other things like homomorphic equation, I guess you cannot really fix this approach, right?
Yes, that is how it seems.
Let me check. Thanks for answering my question. So let me check if there's any other question waiting for us. Maybe I also mentioned a follow-up. Actually, I noticed you have a ongoing work about also investigating the OY proposal from Social Security. Can you share something with us?
So there, so in that case, the Euclidean distance is used again as a sorting metric. So the attack there is that given the Euclidean distance, ideally there would be an infinite number of possible locations for the driver defined by the circle with that radius. However, they use homomorphic encryption and therefore the coordinates are encoded as integers. So if you use a system such as UTM, which maps floating point coordinates to integers, we actually end up with a very few number of lattice points on the circle. And so the number of possible locations are very less and not very large.
Okay, I see. Thank you. So
okay, let's thank the speaker again.
Okay, thank you.
Thank you.
Okay, so yeah, as mentioned repeatedly, we have a Q&A session online, so please join the Q&A session if you want a more intensive discussion. Okay, thank you.
Yeah, thank you.
So thank you, everyone. Thank you, Professor Sharman and Professor Borua, for chairing this session. You can directly join to the author for Q&A session. Welcome back to the next session of the paper presentation. This session is focused on cryptographic constructions, and for this session we have two session chairs, Professor Sanjeeva Prasad and Dr. Nilotpal Chakraborty. During the session, you can post your QA in the chat box of the event platform itself. So over to you, to the session chair. Thank you.
Thank you, Paulami. Welcome to session 8. And we have 3 talks in the session. The first is Exynos, an efficient, verifiable, dynamic, symmetric, searchable encryption scheme with forward and backward privacy. This will be presented by Chiara Marcola. The next talk will be Smooth Zero-Knowledge Hash Functions, which will be presented by Hamid Reza Khoshakhlagh. And the third talk was another use of the 5-card trick, card minimal secure 3-input majority function evaluation, which will be presented by Kodai Toyoda. The speakers will speak for 15 minutes and have 5 minutes for questions and answers. And after the session, they will all break out into Google Meet rooms where you can interact with them and ask them more questions. During the talk, you can always type in your questions into the chat box and I can read them out. And those who are in the live audience will likewise have an opportunity to ask questions. Thank you. Over to you, to the first speaker.
Thank you. Okay. Hello, everybody. I'm Chiara Marcola from TII, Technology Innovation Institute in Abu Dhabi. And today I speak about an efficient, verifiable, dynamic, symmetric, searchable encryption scheme with forward and backward privacy. This work is joint work with Najwa, Xiaojie, and me. So what we are going to see is an introduction on searchable encryption with the basic notion. After that, our scheme in detail, and then a comparison with the state of the art. So what is a searchable encryption? A searchable encryption scheme allows a client to outsource his data to a cloud. And then the cloud can search inside this data. So what we have to do? First of all, we have to build a database that link each keyword to a document. More precisely, each keyword is associated to a set of index, and each index corresponds to a document that contains the keyword. After that, we have to encrypt its database and send to the server. In the server also we store the encryption of the documents. So now, suppose that I want to search a keyword, W, and I want to search all documents that contain in this keyword. So I send the query to a cloud, the cloud runs the search and give back the encryption of either the encryption of the indexes or the encryption of the documents. Now we have also a dynamic set. In the dynamic set, we can also update or delete some document. And this update is in the safe way, so we can do in the encryption way. And so we can modify the encryption database in this way here. Of course, there is always a trade-off between efficiency and security. And if we want an efficient scheme, we have to allow the server to learn something. So for example, the information that the server learns during the setup phase is called size pattern and includes the number of encrypted files containing the keyword. Now, during the search phase, there are other 2 kinds of leakages that is called search and access pattern. The first one permits to the server to learn how many times and when the keyword has been searched, and the access pattern, which file are retrieved. Of course, in the dynamic setting, we have other kind of leakages, but we want to prevent that the server learn any link between the previous search and update document. And this kind of security is called forward privacy. Instead, the backward privacy prevent information leakages from delete data. Also, in this case, we have different kind of leakages that we have to permit. So we have three kinds of backward privacy. The first one is the more safe, relieves the time of matching certain file, the total number of update, and the matching document associated with the keyword. The type 2 reveals also the time of each update. And finally, the type 3 reveals which kind of update is, so if we insert or delete a document. Now, until now, we consider it a server that is honest but curious, but there is also other kind of server that is called malicious server. And this server can send back incorrect or incomplete result. Now, if a scheme is able to detect this kind of behavior, it's called verifiable. Our scheme is the first verifiable dynamic symmetric searchable encryption scheme, which achieve both forward and backward privacy. And in our case, the backward privacy is of type 2. So relieve the time of each update, but not which kind of update is. Now we are going to see in detail our scheme. So our scheme is based on the principle of additive and secret sharing. What does it mean? So we can consider the keyword that is associated with this set of indexes. Each index is obfuscated with a random element. This random element is a secret sharing, and the XOR of this random element is stored to the server side. Then we have another element that is not random, that is needed to reconstruct the secret that is saved to the client side. Okay, so suppose that our keyword W1 is contained into document 1 and 3. Now what we have to do? First of all, each keyword is linked with a secret that in this case is just a string of 1. Then we have to compute 2 secret key that is linking with this keyword. And then we obfuscate the first index. So we choose a random element that is the obfuscated index. We XOR with the secret that is just the string of 1, and we store it in R. After that, we compute the first position with this function that actually is just a hash function that take as input a secret key and R. In this position, to the server side, we store the XOR with the hash function of R and the obfuscate index. After that, we computed the second position with the same function. In this case, the input is just the secret key and the obfuscate index that is different respect here. And in the second position, in the server side, we save the ciphertext that is the encryption of the operation. In this case, is insert because we add the document, and the index that is the index 1 of the first document. After that, we go on with the second index. And what we are going to do, so we do exactly the same. We obfuscate this index with a random element. We update R with XOR with this new obfuscated index. We compute the 2 positions. In the first one, we save the obfuscated index of the third document, XORed with the hash function of the new R. And in the second position, the new ciphertext. To the client side, in this case, we save the link between the keyword and our R, that is the XOR of all the secret sharing. Okay, now suppose that I want to find the documents containing the keyword W1. So the client has to, first of all, find R with in the dictionary, and then compute again the 2 secret key. The second store, and the first one sent to the server with R. With these 2 elements, the server is able to find the first position In the first position, we have this element that stored with the hash function of R. We are able to find the obfuscate index of the document 3. With this index, so obfuscate index, we do two stuff. First of all, we are able to find the position where we store the ciphertext, so the encryption of the index, and then we start to reconstruct the secret. So we XOR it to R, we cut the last part, and we update R. With this new R, we go on, we do exactly the same operation, and we find the second ciphertext. So first of all, we compute the position where we store the VED1. With this, we XOR with the hash function of R. We find again the obfuscate index, in this case of the first index. We find the ciphertext, and we reconstruct the secret. Now the server, because they XOR both of the secret share, find S, that is the string of 1. So it knows that there are just 2 ciphertexts that he have to send back to the client. So send back these 2 ciphertexts, the client with the key is able to decrypt and find the documents. Okay, now we want to update. To update, suppose, for example, that we have the document number 8 that contains the keyword W1. So we want to add it in our database. What we have to do, it's very similar as before. Indeed, we have to find again our R and update it with a new obfuscate index. So we take a random element, XOR in R, and update R. At this point, we do exactly as before. So we compute the 2 positions, Y, so the new XOR between the hash function with the obfuscate index and the encryption, and send to the server. Now the server that have these 2 couples update in position 1 corresponding to the index 8 VIDA, and in position 2 the new ciphertext corresponding to the index 8. Of course, as you can imagine, the deletion is exactly the same. So if we want to delete the document, for example, the document 3, we have to do exactly the same operation. So we have to obfuscate again the index that we want to delete. And the unique thing that we have to change is here. So the operation, instead to put insert, we have to put delete. So in the ciphertext, here we have delete. And then send again to the server the tuple, and the server update the dictionary. Now, the scheme that I present until now is not verifiable, so it's not able to detect if the server is malicious. To modify our scheme is very simple to do it verifiable, because what we have to do, we have to modify just the update and the setup phase, specifically in the encryption. So here in the encryption, we have to add the obfuscate index. So we have the kind of operation, the index, and then we add also the obfuscate index. So when the server gives back the ciphertext, the client is able to reconstruct the secret. And if it's found after all the operation, if it's able to find S, so the string of 1, it knows that the server is not malicious. Okay. Now we are going to see very fast the performance comparison with the other scheme. In particular, some of the scheme. As I already mentioned before, there is always a trade-off between security and efficiency. In this, as you can see, for example, Moneta and Janus, they are, Janus is much more efficient. Indeed, the computation and communication complexity is better than Moneta, but the security here is backward privacy, so it's less secure than the type 1 of Moneta. So now, if we consider just FIDES, MITRA, AURA, and our scheme, that are all schemes that achieve forward privacy and backward privacy of type 2, all of these schemes are not verifiable, indeed, because our is the first one that achieve also the verifiability. And as you can see, these schemes are very similar to our computation and communication complexity. The difference here is the query complexity. Indeed, our is constant and not this. Our query complexity is a bit better. Now, if we focus on Sophos and MITRA and our scheme, for example, so Sophos has exactly like us communication and communication and computation complexity, but is not achieved backward privacy and is not verifiable. Actually,
about a minute to go.
Yes, I almost finished. Thanks. Yes. So actually, Bost also had a verifiable scheme in his paper, but the client storage increase. So now, MITRA in this case is very similar to us, but as I already mentioned, the query is big. Indeed, if we are going to see our two picture here, we can see that the search time per each matching entry Sophos suffer a bit the number of documents. MITRA and our scheme is constant, so it's independent to the matching document. And MITRA is a bit better because for each document, it spends 0.3 microseconds to find, our 0.9. But as you can see here, the query generation time in our case is constant, so is independent to the matching document. Instead, MITRA, for example, is linear, so grow respect to the number of documents. Okay, thank you for attention. And here we have some references. Okay.
All right. Thank you, Chiara. Are there any questions?
Yeah, any questions offline? No questions from the audience. I have only one couple of questions, couple of basic questions. So yes. The first one is that, can you please repeat how you computed R? Probably it was in your slide number 8 or 7.
Yes.
And the second question is that how dependent your scheme is based on the hash function that you used.
Yes. So the hash function that we take is collision functions. Let me check because I wrote. Can I share again the screen or not? It's better to know.
Yes, please. Go ahead.
Okay. Thank you. Because it's more simple to explain in this case.
And he said slide number 8.
Yes, indeed. So let me see if here I write the hash function that we use. Yes, collision resistant hash function with 256 bits. And here, where I compute R, that I guess that is here, the first that I compute R is the XOR between a random element that obfuscated the index and this S that is the secret, that actually is not really a secret because everybody knows that is a string of 1. So when you reconstruct the secret, at the end, you know when you arrive at the end of the chain because you find the string of 1. I hope that I replied to the questions.
Yes, thank you. Over to you, Dr. Prasad.
Are there any other questions? A very quick question which I had is, if you had an honest server, but you had the malicious observer of it, are there concurrency effects, given that many people could be querying the database at the same time, that could reveal some side channel information about how these queries are related to each other? If I have two related sets of queries, and could I be able to get correlations out of that?
Depends. So we are there is some leakages that are permitted. So there are permits and leakages respect, for example, if I ask a query to the previous queries. But is not permit, for example, if I update a document, the server is not able to know this updated with the previous query that I already asked to the server.
Okay, thanks very much.
Thank you.
We're ready to move to the second talk, which is smooth zero-knowledge hash functions. And the presenter is Hamid Reza Khoshaklag. I hope I've pronounced the name correctly.
That's correct, yes.
Go ahead.
So first of all, do you hear me well?
Yes, we hear you well. Could you please share your slides?
Yes. So, okay, is it shared now?
Yes, go ahead.
Okay, great. So, okay, hello everyone. I'm very happy to be here. So today I will be talking about our work, smooth zero-knowledge hash functions, which is a joint work with Behzad Abdulmaliki and Helger Lipma. So let me begin with the notion of smooth projective hash functions, which is the main primitive in our work. So smooth projective hash function, or SPHF, is a cryptographic primitive consisting of some algorithms. There is a keygen that generates a key pair of HK and HP, where HK is a secret key and HP is a public key. And then there are two algorithms, hash and projective hash, that compute a hash value. So hash takes as input this secret key and some statement X and compute the hash. And projective hash takes as input the public key HP and the witness that should correspond to the statement X and output some hash value PH. And if W is the witness corresponding to the statement X, then the two hash values should be the same. That's the correctness property for SPHF. We have also a smoothness property, which says that if X is not in the language, meaning that there is no witness for this statement, so there is no way to compute the projective hash anymore, the hash value should be random. So more formally, a projective hash function consists of 5 algorithms. There is a setup algorithm that generates the language parameters and fix the language and NP language. And we have a hash keygen that takes as input this language parameter and output some secret HK. A projective keygen that takes as input the secret key, the language parameter, and sometimes the statement. So depending on the type of the SPHF we are considering, it may takes as input the statement or not. And finally, it outputs some public key HP. And then we have the hash algorithm that outputs some hash by using the public statement X and secret key HK. And projective hash that takes as input the public key HP and the statement and some witness W. And then if as I said before, the correctness says that for any pair of X and W in the relation, the two hash values should be the same. And if X is not in the language, then the pair of public key HP and this hash value computed by the hash algorithm should look indistinguishable from HP and some random value in the range of the hash function. So it basically says that the adversary, by seeing HP and this hash, doesn't learn anything about, cannot distinguish this hash from a random value. So SPHF has several applications, but the one we are considering mostly is the non-interactive zero-knowledge or zero-knowledge arguments. And what we want to do is to make this zero-knowledge proof, to construct subversion-resistant zero-knowledge proofs based on subversion type of a smooth projective hash function. So let me explain a bit about what is a zero-knowledge proof system in a trust model and what I mean by subversion. So a proof system in a trust model, we have 3 types of players: a trusted party that generate a reference string, a string called a CRS. And because this party is trusted, so both the prover in the left side and the verifier in the right side know that this CRS is generated honestly. And then they interact with together, and at the end, the prover in the left side tries to convince the verifier that the statement X, which is public, is inside the language, inside some NP language. And they use this CRS to check this. I mean, the prover used this CRS to convince the verifier, and verifier used the CRS to check the claim by the prover. And this is what we call a proof system. And then the zero knowledge property states that this flow of transcript between the prover and verifier, it should not reveal any information about the witness of the prover, W. And by subversion, what we mean is that subversion means that now, what if this trusted party is not trusted anymore? And what if this CRS is generated maliciously? So actually, the purpose of subversion zero knowledge is to make sure that what if we reduce the level of trust and see if we can change the model a bit and make the trust a bit less, such that at the end we still have some meaningful notion of zero knowledge and security. And so to see how SPHF that I described at the beginning is related to zero knowledge proof, so I have this slide which show how we can construct honest verified zero knowledge proofs from SPHFs. So the idea is that this CRS generator just generates some language parameter and define the CRS to be the language parameters. And now there is an interaction between the prover and verifier. The verifier generates the key pair of the hash and send the public key HP to the prover. And now the prover compute pH, the hash value pH, by using the witness and send pH to the verifier. And now verifier accept the proof if this pH is equal to the hash of a statement. So by the correctness property of the SPHF, we know that the two hash values are the same if the prover is computing the hash by using the valid witness. So, but the important point here is that it's not really zero knowledge, because we are assuming that the first message from the verifier is generated honestly. And in fact, there is no guarantee that if HP is maliciously generated, then there is no way to make sure that the zero knowledge property holds, or more formally, if we can simulate the hash computed by the prover. So, and that's the purpose of the main motivation for this notion of trapdoor SPHF. Trapdoor SPHF is a type of SPHF which is in the trust model. So now there is also a CRS, a reference S string, that has a trapdoor, and that trapdoor allows to compute the hash in a different way. So to be more formal, there are several algorithms that many of them are similar to smooth projective hash functions. But here in TSPHF, we also have a var HP algorithm that verifies if an HP is generated correctly or not. I mean, it checks if HP is well formed or well defined. And then it computes a hash by using the statement and the trapdoor of the CRS. And now in this case, the zero knowledge property states that this TH computed by the trapdoor should look indistinguishable from a PH that is computed by using the witness. And in this case, we can make sure that the hash value is not revealing any information about the witness. But now, even though this notion looks good for considering subversion, but it's not completely, I mean, here, even though we are removing the trust to the verifier, but we are still, we should rely on a trust to the CRS generator. But so if we consider this as a subversion problem, we are just shifting the problem from trusting to the HP generator, which is the verifier, to trust to the CRS generator. And that's why we define this notion of smooth zero knowledge hash functions. So the notion is very similar to trapdoor SPHF, but here we have two new algorithms. One is so setup hash keygen, projective keygen, and projective hash are the same as before, where HP is similar to the algorithm in trapdoor SPHF. But here we have also var pair, which is an algorithm that checks the well-formedness of the language parameter, and also a subhash, which is similar to the t-hash algorithm in trapdoor SPHF. But we go into the details of this subhash to see how we can simulate the hash value. The properties are similar to trapdoor SPHF, but here we have also subpair smoothness, meaning that a smoothness should hold even if the language parameter is created maliciously. And then the zero knowledge property states that even if HP and the language parameter are generated maliciously, then either we can detect this by these var HP and var pair algorithms, or we can simulate the projective hash. So when we define this notion of SZKHF, we first consider the zero knowledge property in the plain model, which basically it says that for any subvertor Z that output HP, we compute hash 0 H0 or H1 either by a projective hash algorithm or by this subhash algorithm. And then assuming that the verification of HP, where HP passed the verification for HP, for public key HP, then the adversary should not be able to distinguish H0 from H1. But this is a very strong notion because we then show that it's not possible to have this type of zero knowledge property in the plain model if we just use black box techniques. And the reason, I mean, the impossibility is very similar to the impossibility we have for 2-round zero knowledge proofs, because here the simulator doesn't have any trapdoor to compute the proof, to compute the hash. So we have two alternatives for this. We either rely on some trust model, which is the RPK model, registered public key, which is weaker than the CRS model, and then we have also another construction in the plain model, which is based on non-black box assumptions. So I will mostly focus on the last one. I mean, for the construction in the plain model, which uses non-black box techniques. So in this case, we define the subversion. We define this notion of zero knowledge in the following way. We say that for any subvertor Z, there exists an extractor that have a non-black box access to this subverter. So he has the code of the subverter, and by that he can output a function of the HK, kappa HK, and this kappa HK, which is the output of the extractor, is enough to be given to the subhash algorithm to compute a hash. So again, we compute H0, H1. H0 is computed by the projective hash, and H1 is computed by the subhash. And then we give one of these H0 or H1 to the adversary. And assuming that the pair of statement and witness is inside the language, and assuming that HP generated by the subverter passes the verification, then the adversary should not be able to distinguish these two hash values, one computed by a real, based on using a real witness for a statement X, the other is by using the output of the extractor, which is a function of the HK. And then we show that in the RPK model, we show that, which is something weaker than the CRS model, we show that the previous construction of TSPHF is also secure in this model. And in the plain model, we show that we give a construction of sub ZK SZKHF, a smooth zero knowledge hash function in the plain model, based on any SPHF that is constructed from a notion of a diverse vector space that I didn't explain here. It's just a basic framework for constructing SPHF. And finally, we show the security proof in the based on knowledge assumption. We show that subpair smoothness holds based on a new type of decisional Diffie-Hellman assumption, and zero knowledge property holds based on some knowledge assumption that we show in the paper that it holds also in the algebraic group model. So that was my talk, and if you're interested, also the full version is on ePrint, so you can check the full version also.
Thank you, Hamid Reza. Perfectly timed. Are there any questions?
Yes, any questions offline? No questions from this side. Would you?
Do you have any questions?
No,
okay.
Nothing
All
from
right.
my side. Any questions online? You can check.
Yeah. I don't seem to see any questions on the chat. So I'm assuming there are none. Hamid Reza, did I hear you right when you said that you assumed that your language was in NP? That X was taken from a language from NP?
Yes, so we are giving this construction for any arbitrary language, NP language, which means that there is a statement and also a witness. And by that witness, we compute a hash, or by using only the statement.
So I have a sort of silly question, which is, what if you took an X which was from a language in co-NP? Does the same framework play out, or is it somewhat different?
Yeah, I think by NP, I mean just a general language that, I mean, a pair of a statement and witness is enough to define this SPHF for I mean, computing the hash in two different ways.
Okay. If there are no other questions, we'd like to thank the speaker again, and we're ready to move on to the third talk, which is another use of the 5-card trick, card minimal. Oh, good. That's the applause. Yeah. Another use of the 5-card trick, card minimal secure 3-input majority function evaluation. And Kodai Toyoda is going to give the talk. Over to you, Kodai.
Okay. Can you see my screen?
Yes, we can. Go ahead, please.
Okay. Hello, everyone. I'm Kodai Toyoda, a student of Tofuk University. Today, I'm going to talk about another use of the 5-card trick, card minimal secure 3-input majority function evaluation. This is the joint work with Daiki Miyahara and Takaaki Mizuki. Here is the outline of my talk. Let me start with introduction. First, I'd like to talk about secure multi-party computation. Let's consider the case where 3 players have private input bits A, B, and C, and they want to know only the value of a function f of A, B, C without revealing their input bit. The computation that makes this possible is called secure multi-party computation, MPC for short. Card-based cryptography is one of a convenient solution to perform MPC. In this study, we use a 2-card deck of cards consisting of black and red cards whose backs are all identical. Using 2 cards, we encode a Boolean value like this. Black to red represents 0, and red to black represents 1. Based on this encoding, a player can commit a private input to a pair of face-down cards, keeping its value hidden. We call it a commitment to the bit A. If A equals 0, then the left card is black, and if A equals 1, then the left card is red. Now let me introduce 5-card trick, which is the first card-based protocol proposed by Denbor. This protocol takes commitments to X, Y, and 1 additional red card as input, and output X and Y. Assume that there are commitments to X and a commitment to Y, as well as an additional red card like this. This 5-card sequence is the input to the protocol. Then swap the 2 cards of the commitment to Y to make a commitment to bar Y. That is, these 2 cards are a commitment to the negation of Y. In addition, turn over the leftmost red card. Please note that in this case, for each input, the sequence of cards is like this. That is, 3 red cards are cyclically consecutive, i.e. the first, second, and fifth cards are red, if and only if x and y equals 1. Then apply a random cut to the sequence of 5 cards. A random cut is a shuffling operation. Let me show a video of a random cut. This shuffle shifts the positions of the sequence without changing the order. And if a random cut is applied to a sequence of 5 cards, it transitions in these 5 cases, each with a probability of 1/5. These sequences are all identical up to rotation. Applying a random cut, we get the following state. Then reveal the 5 cards. If the 3 red cards are cyclically consecutive, we have x and y equals 1, and otherwise we have x and y equals 0. And let me explain our target. As you might see, 5-card trick is easy to understand and it can be used for teaching lay people the concept of secure multiparty computation. But many lay people would consider that such a secure 2-input and computation may be somewhat useless. Because once Alice having the private bit of x equals 1 knows the result of the computation, she gets to know Bob's bit. Of course, this is inherent, but it would be worthwhile to find more suitable functions for educational purpose. And in this work, we consider the 3-input majority function, majority of ABC, as a promising function defined like this. Now, I'd like to explain 3-input majority protocol in card-based cryptography. Given 3 commitments to bits A, B, and C, together with some additional cards, players apply a series of operations such as rearranging, shuffling, and turning over cards to get the output. And a protocol whose output is given with a commitment is called a committed format protocol, and a protocol whose output is not given with a commitment is called a non-committed format protocol. Now let me show the existing 3-input majority protocols. In 2013, Nishida et al. Presented the first 3-input majority protocol using 8 cards. And since then, several other majority protocols have been proposed. Please remember that the first protocol and the last protocol do not use private operations. And allowing private operations is a strong assumption that a player may manipulate the cards privately, say behind their back, while making sure that the other players do not see the movement. So we focus the protocols that do not rely on any private operations. There are 2 existing protocols without using private operations. Both protocols need 8 cards. That is, they use 2 additional cards like this, so it has been an open problem to reduce the number of required additional cards. Now let me present our contribution. We construct a 3-input majority protocol with 6 cards. This is the first card minimal 3-input majority protocol, and card minimality means to use no additional cards. Also, we show how to transform our non-committed format protocol to committed format 1. Due to time constraints, I will skip this part. Now let me present our card minimal 3-input majority protocol. We constructed a 3-input majority protocol with 6 cards. Let me explain the idea behind our majority protocol. We make use of the following simple facts on the 3-input majority function majority of A, B, C. If A equals 0, then majority of A, B, C equals B and C, and if A equals 1, then B or C. As we can compute B and C by using the 5-card trick, and we need to how to compute B or C. To solve this, we propose the 5-code OR protocol by modifying the 5-code trick slightly. I'll explain these 4 variants of 5-code trick. The first one is let-based AND protocol. This is AND protocol with a let code as an additional code, and this protocol is exactly the same as the 5-code trick. The second one is let-based OR protocol. This is OR protocol with a let code as an additional code. And let us write commitments to X and commitments to Y using X0, X1, Y0, and Y1 like this. Then rearrange the 5 codes like this. In this case, 3 let codes are cyclically consecutive if and only if X or Y equals 1. So X or Y can be computed by applying a random cut. The third one is block-based AND protocol. This is AND protocol with a block code as an additional code. And first, rearrange the 5 codes like this. And in this case, 3 block codes are not cyclically consecutive if and only if X and Y equal 1. So X and Y can be computed by applying a random cut. The last one is block-based OR protocol. This is OR protocol with a block code as an additional code. First, rearrange the 5 codes like this. And in this case, 3 block codes are not cyclically consecutive if and only if X or Y equals 1. So X or Y can be computed by applying a random cut. These 4 protocols satisfy the following relationship. Let's consider the let-based AND as a start. If the second and 5th codes are swapped, the let-based OR is applied. And if the first code is replaced with a block code, the block-based OR is applied. And if both operations are performed, block-based AND is applied. We use the relationship between these 4 protocols to construct our majority protocol. First, place the commitments to A, B, and the negation of C. In the case of A equals 0, please recall that majority of A, B, C equals B and C, and if A equals 1, it is B or C. And let us apply a random cut to the second through 6th codes. Since the let-based AND will be applied if A equals 0 and the block-based OR will be applied if A equals 1, we can obtain the value of majority function. However, depending on whether the output is let-based or block-based, the value of A will be leaked. To resolve this issue, we randomize the state so that if A equals 0, either the let-based AND or the block-based AND is applied with equal probability, and if A equals 1, either the let-based or the block-based OR is applied with equal probability by applying the random bisection cut. A random bisection cut is shuffling operation that bisects a sequence of codes, swaps the 2 halves at random as like this. Therefore, the shuffle results in 2 possible cases, depending on whether the 2 halves are swapped or not, each with a probability of 1/2. After applying a random bisection cut, we have these 4 possibilities. Then if we apply random cut to the second through 6th codes, then either the let-based AND or block-based AND is applied when A equals 0, and with the equal probability. And either the let-based OR or block-based OR is applied when A equals 1. So the value of A cannot be leaked, while the value of majority function can be obtained. Thus, we can compute majority of A, B, C. Here is the description of our majority protocol. And step 1, first place a commitment to A, a commitment to B, and a commitment to the negation of C like this. And step 2, rearrange the codes like this. And step 3, apply a random bisection cut to the leftmost 4 codes. After applying the random bisection cut, the sequence of codes will be one of these 2 ways with a probability of 1/2 for each. And step 4, rearrange the codes like this. Now, if a random cut is applied to the second through 6th codes, one of these 4 protocols will be applied. And step 5, apply random cut to the second through 6th codes. And step 6, reveal all codes to obtain the output. And first, reveal the first code, and next, reveal all the remaining 5 cards, and then the sequence of cards will be one of these. In the case of false cards is red, if the 3 black cards are cyclically consecutive, we have majority of ABC equals 0. Otherwise, we have majority of ABC equals 1. In the case of the false card is black, if the 3 red cards are cyclically consecutive, we have majority of ABC equals 1, and otherwise we have majority of ABC equals 0. This is our majority protocol. As you can see, the number of shuffles in this protocol is 2. Next, I'll give a description of our majority protocol in a formal way based on the computation model of card-based cryptography. In card-based cryptography, there are 3 main operations performed on a sequence of cards, namely permuting, turning, and shuffling. Let us assume a sequence of n cards. These operations are denoted like this, and pi is a permutation applied to the sequence of cards, and large T is a set of indexes indicating that T's cards is turning over for every T. The large pi is a permutation set, and the large F is a probability distribution on large pi, indicating that pi is drawn according to large F and is applied to the sequence of cards. And note that nobody knows which permutation in large pi was applied. If the probability distribution large F is uniform, we may omit it. And here is a pseudocode for our majority protocol. As you can see, this protocol is very simple. And next, let me move on to correctness and security. We make use of the KWH3 to verify the correctness and security of our proposed protocol. KWH3 makes it possible to visualize the state transition of the cards like this. And if one can write the KWH3 satisfying some properties for a protocol, then it automatically implies that the protocol is correct and secure. We can write the KWH3 of this protocol satisfying the required properties like this. Thus, our protocol is correct and secure. Finally, I conclude this presentation. In this work, we constructed the first card minimal linked majority protocol using only 6 cards. And that's all. Thank you for listening.
Thank you very much, Toyoda-san. Are there any questions?
Yeah, so any questions offline? Not from the audience. I have a couple of questions. So first of all, there is a comparison table that you showed probably in slide number 21. And so my question is that you said that the runtime of those algorithms, the existing algorithms and yours as well, is finite. So can you quantify that number a bit? What do you mean by finite here?
Sorry, could you repeat your question?
Yeah, so when you say runtime is finite, what do you mean by finite here?
Yes, finite means this protocol finished a fixed number of operations.
So is it like that for all these 5 protocols?
Yes. I skipped this protocol, our Las Vegas protocol, but there is Las Vegas runtime protocol. This means it has a loop in the protocol, so it doesn't terminate within a fixed number of operations.
Yeah, perhaps you should use the word definite or bounded. And I guess in the other one, you're saying that it's not definite, but it terminates with some kind of distribution given by Las Vegas, right? Some kind of random distribution, random number which follows a distribution. Is that what you mean?
Yeah. Sorry, could you repeat?
Yeah, I think when you say finite, you probably want to say definite or bounded.
Yes.
Yeah. Okay. Are there any further questions?
Yeah. My next question is actually related to your slide number 53. So, is it possible to share the screen? Share your screen again?
Yes. 53.
53. 53.
Okay.
Yeah. So in this place, in this case, in step 2, when you rearrange the cards, so the first card
Yes.
always remains to be the same, right?
Yes.
So, I mean, just out of curiosity, it's probably a very primitive question. So, is it possible that this scheme will lead to a partial information leakage?
Sorry, I can follow you. So, could you repeat your question?
Yeah. Okay. So, my question is that since the first card is not rearranged, it kind of is the same. So, is it possible that this scheme will result in an output which is, which will lead to partial information leakage?
Yes. So, because step 3, we apply a randomization cut. So, first card is swapped to third cards in probability 1/2. So, information cannot be leaked.
All right. Thank you. That's all from my side. Over to you, Professor Prasad.
Yeah. Are there any further questions? Well, this was a fascinating talk, and thank you very much. I think we've a few minutes ahead of schedule, but we've come to the end of the session. And I'd like to thank the speakers again. And I'd like to remind the audience and the speakers that there are breakout Google Meet venues where you can interact with the 3 presenters and ask them further questions. And once again, thank you all. Thank you very much for attending, and thank you to the speakers. That was a wonderful session. Thank you very much.
This is a time for short break of 15 minutes. We will be right back to the next session at 6:30 p.m. IST sharp. Thank you. Welcome to the last session of paper presentation. This session focuses on blockchain, and for this session we have with us two of the session chairs, Professor Vishal Saraswat and Professor Abhishek Sharma. So over to you to the session chair. Thank you.
Hi, welcome to the last session of Indocrypt. It's on blockchains, and we have three very interesting papers on lapse time consensus protocols, on time release cryptography from minimal circuit assumptions, and succinct publicly certifiable proofs. Or can a blockchain verify a designated verifier proof? So we'll start with the first paper on elapsed time consensus protocol by Mike Bauman, Debajyoti Das, Avrabdeep Mandal, and Hart Montgomery. And Debajyoti will present the paper. So on to you, Debajyoti.
Hello, everyone. Thanks for the introduction. Now I'm going to talk about our work on elapsed time consensus protocols, which is one class of consensus protocols for blockchains. Blockchains can be thought as a distributed database or distributed ledger. Let's look at it with an example. If you are looking at a centralized database, for example, a bank database, the bank controls the whole database. All the client data, all the transactions are controlled by the bank, and all the update, delete, addition, all are done by the bank itself. However, in case of distributed databases, in this example, you can see there are 4 nodes. All the 4 nodes collectively control the database. No one node has complete control over the database, and the clients interact with the database by talking to those nodes. And how the nodes keep the data? Each node has a copy of the database, especially in case of blockchain. And data is stored in the form of blocks. So basically, they are data blocks with a pointer to the previous block. So they're literal data blocks, and they're chained together. And that's why they are called blockchains. And the nodes need to use a consensus protocol to agree on the current 2 state of the system at any given point of time. With that premise, let me give you an overview of what I'm going to talk about in this presentation. First, I'm going to talk about what are elapsed time consensus protocols, or why even think about them. Then I'm going to talk about a variation of elapsed time consensus protocols with trusted execution environment. And then I'm going to talk about another variation where you don't have trusted execution environments, or they can be compromised. And then that is with a primitive called Z-test. And then I'm going to discuss about the security of elapsed time consensus protocols with Z-test, which is one of the main highlights of our paper. And then I'm going to talk about the implications of our work. So before I move to what are elapsed time consensus protocols, let us look at one of a really famous consensus protocol, which is proof of work. Proof of work protocols are scalable to tens of thousands of participants because of its low communication overhead. In an optimistic case, the communication overhead is order of n for n participants per new block. How these protocols work? Again, let's look at it with an example. Suppose there are 4 nodes, node A, node B, node C, node D. They all try to solve a cryptographically hard problem. And suppose node A solves the problem first, then node A is the one who releases the next block. And then node A broadcasts the block to everyone. And that's how every new block gets released. And that's how they achieve consensus among who becomes the leader for every round. However, it comes with a caveat. Each node is solving a cryptographically hard problem, and that is high energy consuming. For example, the power consumed for Bitcoin proof of work network in January 2019 was around 40 terawatt hour, which is comparable to the power use of a small country. And of course, we want to save the environment, we want to have less carbon footprint, and we don't want to pay for electricity bill. That's why we want to look at low power alternatives. There are few alternatives. One prominent alternative is BFT consensus, or a Byzantine fault tolerant consensus. However, these protocols have high communication overhead, order of n square per new block when there are n participants in the system. So if there are 10,000 participants, the protocol will take a huge time to reach consensus. And that's why these protocols does not scale well with large number of participants. Also, there are proof of stake systems, but proof of stake systems either internally use BFT-based consensus, for example, Ouroboros protocol, and that will have high communication overhead. And there is another variation called chain-based proof of stake systems, but they have either strong security assumptions or they lack formal security proofs. And then there comes proof of elapsed time. Till now, these protocols, for example, proof of elapsed time or proof of lock, these protocols did not have any formal security proof. And of course, you don't want to use any protocol where you don't know what security you are achieving. Even though these protocols are low energy consuming, have low communication overhead, still you don't have the confidence to use them. But that is until now. With our work, we fill that gap and we provide formal security proof for these elapsed time consensus protocols. So what are elapsed time consensus protocols? So in literature, there are mainly two elapsed time consensus protocols. One is proof of elapsed time, or POET, and another is proof of lock. These are similar protocols, but not exactly identical. But what we do in our paper is we get rid of their nitty-gritty details. For example, bootstrapping, how they solve collision, etc. And we define a generalized version of them. In both protocols, proof of work is replaced with randomly generated delays. Again, how that works, let's look at it with an example. There are 4 nodes, node A, node B, node C, node D. In a given round, node A generates a random delay, say 3, following a probability distribution. Node B, using the same probability distribution, generates a delay 6. Node C generates the delay 6, and node D generates the delay 5. Since node A has the least delay, then node A is allowed to publish the block, and node A broadcast it to everyone. This protocol works perfectly if all the nodes are honest and all the nodes know that each one of them are honest and the delays are generated correctly. But you cannot trust that. And that's where the trusted execution environment comes into picture. For example, in proof of elapsed time protocol, they use Intel SGX. And Intel SGX, that trusted execution environment, proves that the delay has been generated correctly. And other protocol parties can verify that. And since we are introducing trusted execution environments and everyone has to identify that, it inherently implies that it is a permission setting. How this works? A node will run the protocol program along with a trusted execution environment inside it. When the node program needs to generate a delay, the node program will query the TE. Then the TE will pick the delay from the specified probability distribution specified by the protocol description. And TE will wait for that amount of time. And then TE will provide the delay along with a delay certificate to the node program. And now the node program can publish the latest block with the delay certificate so that the others can verify. Unless someone else has already published a block for that round. If someone else has published the block, then this node program does not need to publish the block because the other node is the winner. And the same program is run by every node, and that's how it achieves consensus. However, as you can see that the trusted execution environment needs to have access to a trusted timer to at least to know that the delay is correct. That's why we talk about two versions of elapsed time consensus protocols. One, where the trusted execution environment have access to trusted timers, and another one where probably the trusted execution environment doesn't have access to a trusted timer, or the trusted execution environment itself can be compromised, or you probably have no TEs in the system. And we formally analyze the security for both the variations. Also, till now, there was no formal description of the proof of elapsed time protocol by Intel, and our paper or our work can be considered as the first formal description of that protocol. And what security properties do you want to achieve? First is common prefix property, which means we want the honest parties to eventually agree on a common chain. Otherwise, there is no consensus. Also, we want the chain to grow at a certain rate. Otherwise, the protocol will stop. And we want a constant fraction of blocks in the accepted chain to be generated by honest parties. Otherwise, you cannot guarantee the quality of data in the blockchain or the correctness of the data. And the security of elapsed time consensus with trusted timer becomes really straightforward. If the trusted execution environments are incorruptible, then it achieves the exact security properties as Bitcoin. With exactly same parameters, with exact same assumptions. The property that it achieves is with an honest majority of players, it achieves with overwhelming probability the desired security properties that we want, namely common prefix property, chain growth property, and chain quality property. However, as I mentioned before, that TEs might not have access to a trusted timer, or some TEs are susceptible to attacks. For example, Intel SGX is susceptible to attacks like Spectre or Meltdown. And to defend against such attacks in our elapsed time consensus protocol, we need a construction called Z-test. What happens in Z-test? So Z-test is a verification which verifies that an honest party accepting the chain verifies that some other party has not generated too many blocks in a small amount of time in that chain. So that what it achieves, it effectively stops an adversary from concentrating high number of adversarial blocks in a small amount of time. And honest parties are highly unlikely to generate too many blocks in a small amount of time. So honest parties are affected with negligible probability. And with those facts, what we can prove for elapsed time consensus with Z-test. Elapsed time consensus with Z-test, also we can prove that with an honest majority of players, it achieves with overwhelming probability the desired security properties, namely common prefix, chain growth, and chain quality properties. Then what do we lose? The world cannot be all good. It is provably secure only in permission setting compared to Bitcoin, which is provably secure in public setting. Also, elapsed time consensus with Z-test requires more honest parties compared to proof of work system, or even the elapsed time consensus with trusted timer version to achieve the same level of security. So that is the trade-off that is there. And now I'm going to talk about the implications of our results. With our results, we basically achieve a provably secure, scalable, decentralized database without high energy consumption or without high communication overhead. However, the trade-off is security is only in the permission setting, and we can tolerate much less number of dishonest parties compared to proof of work systems. In our case, we can tolerate only 33% dishonest parties, but proof of work can tolerate up to 49%. For recommendation, we recommend using the system with TEs and Z-test. So we know that there are only few dishonest parties, and then we get really good security. With that, I'll finish my talk. Thanks for listening, and I'll open the forum for questions.
Thank you, Devajyoti. Do you have any questions? In the chat, I don't see any questions yet. If anybody has, please put your questions in the chat. In the live feed, do we have any questions?
Let me ask to the participants if, yeah, okay. Yeah, there are some questions.
Hello. How that delay will be get calculated? Means how can we find that delay? Can you give some light on that?
The delay is picked from a probability distribution. In case of proof of elapsed time protocol, it is from an exponential distribution. So you pick a random number from from exponential distribution, and that will be the delay. And since it is generated by the TE, and TE generates the certificate, so the other parties, when they receive a block and the delay, they know that the delay is generated from this probability distribution by the TE. Does that answer your question?
Okay. Okay.
Any other questions? Okay. I don't think there are any further questions.
On the chat also, I don't see any questions. I have a question. So when you have been talking about this power consumption, you have been mostly talking about giving the example of Bitcoin, but Bitcoin is not a permission setting, right?
Yes, that's right.
So
Bitcoin is a public setting.
now let's say you have a distributed protocol, any maybe using Hyperledger or something which is in permission setting.
Yes.
Then what is the comparison on the power?
It depends on the number of participants in the network. Of course, it will be as huge as Bitcoin. But independent of the number of participants, in proof of elapsed time protocols, you don't have to solve the hard cryptographic hard problem. And so you are so that is the saving that you have when you are using these low power alternatives.
And what about the proof of stake?
In case of proof of stake, there are two variations. One is one kind of variation that uses internally it uses BFT consensus. And in that case, it's almost equivalent to using BFT consensus. And in another version, which is chain-based proof of stake, there are right now I don't have specific examples in my mind, but in those protocols, either they have strong security assumptions like some existence of some semi-trusted parties, or they lack a formal security proof. So that's why
here in TE you have this in a way strong security assumption that you need the trusted execution environment.
Yes, and that's why we mostly highlight on Z-test, not the TE.
Okay. All right. So we still have a couple of minutes if anybody wanted to ask questions. But so if you have a question, you may really want to type it now, bring it now. Looks like we don't have any questions, Devajyoti. Thank you for the talk. Hopefully, you will be able to do more progress on the topic and maybe provide some more numbers.
Just one quick question.
Yeah.
Regarding this, you are saying that the cryptographic hard problems, is it that it is the integer factorizations, discrete log problem, or Diffie-Hellman problem? Are you saying to that?
And none of them. In case of Bitcoin, it's solving a hash. So you have to find a nouns which will produce a specific kind pattern of hash. And that is since hash functions are difficult to pre-image resistant, you have to actually keep solving hash for many nounces, and that is that's how you prove that you have done some work. Does that answer your question?
Yeah.
Okay. Thank you, Devajyoti. And now we move to our second presentation of the session. It's on time release cryptography from minimal circuit assumptions, and by Samuel Jacks, Hart Montgomery, Razwan Rosie, and Arnab Roy. And Samuel Jacks will do the presentation. Yeah.
Hi. So that summarizes sort of what this talk is about, time-release cryptography. And our goal was to use, sort of lower the assumptions we need to make cryptographically. To give some background about what that means, in cryptography, we often focus on problems that are either infeasibly hard, so that they give some security to a scheme, or efficient to use, so that they're sort of polynomial time. But in a lot of cases, we want problems that we can solve in practice, but they're difficult in some way. And Bitcoin's proof of work is a great example of this. And Bitcoin's proof of work also highlights something else, which is that if you have more hardware, you can solve the problem faster. So if we imagine a big pile of GPUs compared to a smartphone, and they're both trying to mine Bitcoin, the GPUs will easily mine all the Bitcoin. What we want instead is a sequential function for certain applications. And so this will be hard in the same way. So we know it takes some non-trivial time, but where we cannot speed it up with more hardware. So the big pile of GPUs runs just as fast as a smartphone. We can formally define this by two parameters, TA and TC. So we say that this sequential function is sequential for this larger sub-exponential parameter, capital T, where sort of honest users that have a polynomial amount of hardware can iterate this function T times in time that's proportional to T with this proportionality constant T sub C. But an adversary who has a lot more hardware trying to iterate it T times is still computing it in time proportional to T. And there might be some difference in this proportionality. They might be able to shrink a little bit, but not too much. And these can form the basis for all kinds of time-release cryptography. So these could include time lock puzzles, verifiable delay functions, or proofs of sequential work. And verifiable delay functions in particular have all kinds of applications in blockchain recently, such as verifiable lotteries, different kinds of consensus, maybe resource-efficient blockchains. So there's been a lot of interest in verifiable delay functions in particular, and of course you'd need some sort of sequential function to make one. And there's two main families of verifiable delay functions right now, based on either groups of unknown order or using any sequential function and throwing zero knowledge proofs on it. For groups of unknown order, the main idea is that if you square repeatedly, this should be sequential. So if I want to square T times and compute x to the 2 to the T, I shouldn't be able to do this any faster than just T squarings in a row. Now you can see that if we knew the group order, we could compute 2 to the T mod the group order and do this quickly. But if we don't know the group order, then this seems to be sequential. And there's good ways to verify this. And this seems like a fairly good solution. It's practical and it's probably completely fine. But our approach was trying to reduce the assumptions as much as possible. So some issues that you might raise with this is that, firstly, the squaring might not be sequential. It's a new assumption, and it hasn't been unconditionally proved to be related to any existing assumption. So we might live in a world where factoring is hard, but iterated squaring over an RSA modulus is actually can be parallelized. And in fact, we kind of live in this world because we can parallelize this squaring operation, but just very badly. And finally, it's not quantum secure because you can find the order of any group with a quantum computer. Our construction isn't either, but we just sort of, we're thinking about issues with this. The other thing that we could do to make a VDF is take any sort of random function and use snarks. So we can assume that a hash function is sequential if we just iterate it. So we apply the hash to the hash and we do this T times. And if we're in the random oracle model, this is provably sequential since every output is random. And to verify it, sorry. To verify this, we need generic snarks, and just sort of an argument of knowledge. And this sort of creates kind of a conceptual issue, which is that we can prove that these functions are sequential in a random oracle model, but this treats the hash function as a black box. But to use these zero knowledge proofs, we need to sort of open up this hash function and treat it as an actual circuit. And so this is kind of these feel kind of conflicting in a way. And this isn't a big issue, and I think it would be fairly reasonable to do this anyway. But basically our motivation was, what if you found all these arguments very convincing and you wanted something, a much better guarantee on your sequential function? What can you do? So what we came up with was, starting from fully homomorphic encryption, we give a construction that will be sequential if there exists any sequential function. So for time-release cryptography to work at all, we'll definitely need some sequential function to exist. And the nice part about our construction is we don't need to know what this other function is, and our construction will be sequential. To explain, kind of sort of give some background on where this idea came from, this actually comes from proofs of knowledge for lattice systems. So imagine we have a function f, and we know that there's at least one very difficult input, but most inputs are quite easy. So imagine our adversary has this huge cluster of computers, and we want to force them to take a lot of computation. If we give them a random input x1, probably it's quite easy for them to compute f of x1. And maybe some x2, it's also very easy. But there's some hard input x3, and if we gave it to them, even their huge cluster of computers would have trouble. The problem is we might not know what this difficult input actually is. So we can't give it to the adversary and force them to do all this computation. The idea is that we encrypt everything and make the adversary do everything with fully homomorphic encryption. So first we would encrypt the input, then give it to the adversary. And the adversary basically doesn't know what they're working with, so they have to sort of work in the case where it was the hardest input. So they produce some output and we can decrypt it. So they've equivalently computed f, but they're not sure how to compute f. They really sort of have to do a worst case circuit. And this is a little abstract, so I'll show how we construct a sequential function from this idea. So recall, here's the definition. We want a function where to iterate at t times, the time to do that must be proportional to t, no matter how much hardware you have. And from this, we can get a VDF. So imagine that we actually knew some sequential function. So they exist, we can write it down, we can write a circuit for it. Then it's very easy to make our VDF, we have a sequential function, there's nothing to do. And we have a guarantee based on the definition that the adversary must take time must take time t to compute f t times. From there, we use universal circuits. And this is a circuit that takes two inputs. One is sort of a regular bit string, and the other is a description of another circuit. And when you compute the universal circuit on the description of a circuit and an input, it has the same output as actually computing that circuit on that input. So it computes any circuit given a circuit as input, like a universal Turing machine or any sort of other universal computational device. So we change our sequential function slightly. And rather than computing the function directly, we write it as a circuit and compute the universal circuit with our sequential circuit as input. And because this gives the same output as a sequential function, then by definition, the adversary can't run faster than t. And maybe the honest users are running a little bit longer, but not too much longer because there's fairly limited overhead for a universal circuit. From there, we use fully homomorphic encryption. So what this does, homomorphic encryption allows us to encrypt data and then evaluate circuits on encrypted data so that when we decrypt them, it's the same as evaluating the circuit on the plaintext. But the nice part is to evaluate, you don't need the secret key. So anyone can evaluate, but you can only decrypt with the secret key. So what we do is the entire previous construction, but homomorphically. So we encrypt the input and then have the adversary evaluate the universal circuit on that input. But critically, we also encrypt the description of the circuit itself. So that's why we needed the universal circuit, so that we could encrypt our sequential function. And again, because at the end, we could decrypt the value, this is equivalent to computing the sequential function, and so the adversary can't do this in faster than time t. But now the adversary thinks to themselves, all they were given were 2 encrypted strings. How did they know we actually gave them a sequential function? What if we gave them a different function? Would they be able to cheat? So here's sort of their perspective. Thanks to the snarks, everyone can verify their output. So they need to compute things correctly. They can't cheat by computing a different function, even though they don't know the function. If the encrypted input was really a sequential function, there's nothing they can do. By definition, they can't compute it any faster than time t, even with all of their hardware. So that doesn't help them at all. If we'd given them a different function, then maybe there's some way they could parallelize and still get a correct answer. But the adversary's central problem is they cannot decide which situation they're in because their input was encrypted. So they have to do some computation that will take at least time t. Otherwise, they break semantic security of the homomorphic encryption. So what we actually do in our construction that we defined is, rather than encrypting a sequential function, which we don't actually know, I can't actually tell you if something is sequential, we just encrypt 0. And even though it's not sequential, we can prove that the adversary has to take as much time as a sequential function. Otherwise, they've broken semantic security of the FHE, because if they're computing it faster, we know they've sort of detected that we've encrypted 0 rather than a sequential function. So this construction at the end no longer needs knowledge of the sequential function. We can just instantiate this with things that we know how to do already. There's already constructions for universal circuits and for fully homomorphic encryption. So in some sense, this one really exists. You really could program it. We didn't, because it's hopelessly impractical at this point. The overheads of the homomorphic encryption and the universal circuit are polynomial, but they're quite big. So this was mainly a sort of a theoretical idea on how a sequential function could be made in this way. In the full paper, you can see we account carefully for all of the overheads. We look at different computational models for sequential functions and when certain inputs could come in. And we look at how this applies to the actual applications of sequential functions, like VDFs. I think a big takeaway from our talk and our work is that this tool to use fully homomorphic encryption to take a worst case problem to an average case problem, I think is quite a powerful tool. Basically, anytime you have a worst case assumption, if you encrypt everything with fully homomorphic encryption, then you can kind of force an adversary to work with the worst case, even based on an average case scenario. And so if you find yourself in this kind of situation, I recommend thinking of fully homomorphic encryption as a tool that can maybe help. Thanks for listening, and here are the references.
Thank you, Sam. Do we have any questions from the online audience? I don't see any in this chat.
Any questions? No such question from the hall.
From the live audience. Okay, so maybe I'll ask a question, and meanwhile, if there are more questions online, they can come. So Sam, my question is this, when the adversary does this evaluation of the circuit, the output is still encrypted, right?
Yes.
So now they just deliver the encrypted output, and let's say I'm the one who challenged. So I decrypt and verify if they did the job correctly, right?
In our case, we imagined a scenario where you wouldn't decrypt the output, because if the circuit is all zeros, then you should be getting all zeros out. We imagine sort of like with the hash function, you take a zero knowledge proof, a generic zero knowledge proof, and put that on top of all of the other computations. So you're doing a zero knowledge proof that you did the homomorphic evaluation correctly.
So they find evaluation correctly. That in this sense, the adversary is going to provide that. Was that your thing?
Sorry, could you repeat that? I think your question cut out for
me. It could be maybe my internet messed up. So the question is this: like when we are doing this scenario with the adversary, but whether it be adversary or whether it be a correct evaluator, they do the evaluation, and at the end they need to provide a proof to us that they did the evaluation correctly. What is happening there?
Yeah. So to prove that it's sequential, then just by definition we want them to output the correct answer. Otherwise, sort of they haven't correctly computed it. If you wanted to use
that's
this,
my question. That how do I know that they have done without decryption? How do I know that they have output the correct answer?
So what you would do is you would use since you know the circuit for the evaluation that they have to perform. Sort of each instance of the homomorphic evaluation is some circuit that everyone knows. You can ask for a generic proof that that circuit was computed correctly using snarks. And so this would be the same. Basically, it's the same construction as building a VDF out of a hash function, where you would look at the circuit for the hash function, and you would verify it by simply verifying that they computed the circuit correctly, and you can kind of incrementally verify using these constructions. And ours really isn't different from the hash function case. We're just using this rather complicated construction kind of to act like a hash function. And the benefit is really just a theoretical guarantee that where a hash function might not be sequential, ours must be as sequential as the most sequential hash function.
Yeah. Well, I think, Anwar, we still have 2 more minutes. Any other questions on the chat?
Okay, I have a small query. I want to know that proof of concept which you have mentioned, is it possible to implement in non-time series sequences or non-time series applications also?
I think our particular application I'm not sure that it would be helpful outside of time series applications, but I think very similar constructions could be useful elsewhere.
Okay, thank you.
Yeah, it seems like an interesting work, and given that right now it is completely out of bounds for actual implementations, so I'm guessing there is a lot of options for the people to come here and break their heads and try to make it useful. Practical. So there is a lot of, in that sense, it opens up a lot of possibilities for a lot of research. So, yeah, governments, it seems interesting to me, and I think if we can somehow work on this, right now we are using this universal circuit. If we can work on hiding our circuit without using a completely generic universal circuit, maybe that can start to make it more efficient. Okay, with that in mind, I think let's thank Sam, and we can move to Hamid Reza. So this is our last paper of the last session. So this is the last paper to be presented at Indocrypt, and the paper is Succinct Publicly Certifiable Proofs, or Can a Blockchain Verify a Designated Verifier Proof? I've read the paper. I found it very interesting and hope the audience also finds it equally interesting. So this paper is by Matthew Campanelli and Hamid Reza Khoshklag. And Hamid Reza will present. Up to you, Hamid Reza. Are you on mute, Hamid?
Sorry, I think I was muted. Do you hear me?
Okay, go ahead. Yeah, we can hear you now.
Okay.
Go ahead.
So thanks, Vishal, for the introduction. So I'm happy to present my second paper. So I will be talking about our work. It's called Succinct Publicly Certifiable Proofs, or can a blockchain verify a designated verified proof? This is a joint work with Matthew Campanelli. So, okay, let me begin with the notion of argument system in the trust model. So in this model, we have three types of parties. We have a trusted party, and then we have a prover and verifier. The prover wants to convince the verifier that some statement X is in some language. And then there is a trusted party who generate a string. It's called the common reference string, give this string to both the prover and verifier. And they use this string to run the protocol. And at the end, the verifier decide to accept the proof of the prover or just reject. And then in argument system, we have completeness property, which says that an honest prover can always convince an honest verifier. Soundness, which says that a dishonest prover should not be able to convince the verifier with a non-negligible probability. And then the type of argument system we are interested in this work are of type non-interactive, meaning that there is only one flow of communication between the prover and verifier. So the prover just send send a proof in one flow of communication to the verifier. It's zero knowledge, meaning that the proof doesn't reveal any information about the witness, and in fact any information except the fact that the statement is in the language. The proof is succinct, meaning that it's polylogarithmic in the size of the statement and witness, and it's a proof of knowledge, meaning that at the end we can make sure that the prover already knows the witness. Or this is something which is called ZK snark, zero knowledge snark, and we have two types of snark. One is called publicly verifiable, and the other is called designated verifier. So in publicly verifiable snark, the trusted party gives one single string called CRS to both the prover and verifier, and they use this unique string to verify the proof. The prover and verifier use the same string, but in designated verifier string, the string is different. So there is a public string called the CRS that the prover use, and the verifier use a string which is not public anymore. It's something designated to the verifier, and by that string, the verifier can verify the proof. And it is important that now the soundness property of the argument is it holds only if we assume that the prover doesn't know this secret string VRS. And then the motivation for introducing this notion of ZK snark is their application in this decentralized network. So if we consider the first generation of cryptocurrencies such as Bitcoin, the type of privacy they provide is not very good. So actually, you can see everyone's balance and how they spend, how the people spend their money. But then we have in the next generation, we have cryptocurrencies with much better privacy. So in fact, they hide all this information about the transactions and keep the privacy of the users by using this primitive, the ZK snark. And one important property of this ZK snark is that they should be publicly verifiable, meaning that when a party approver publish a proof, everyone should be able to verify if the proof is correct, is valid or not. And the reason is that there is usually a consensus that all the parties should have a consensus on the fact that whether the proof should be accepted or not. And for that, it's it's more efficient to have a proof that is publicly verifiable and all the users can prove. Otherwise, the prover should send one proof to every party, which is something very inefficient. And then the question we ask is that how we can construct this type of publicly verifiable snark. So we know that there are some restrictions, some requirement. For example, we should use non-standard assumptions because of some impossibility results. But the question is that can we construct this type of publicly verifiable snark in a constrained setting where we require post-quantum security, which means that we cannot use pairing-based snark anymore because pairing is not post-quantum. And the assumptions to be as nice as possible, meaning that no random oracle. We have several snark that are based on random oracle. So no random oracle, no pairing, and also no non-standard assumptions such as obfuscation, for example. And the question is, can we construct publicly verifiable snark in this setting? So we know how to construct designated verifier snark in this setting, but we know that it's not enough for our application, that we need something which can be verified publicly. But now the question is how this publicly verifiable snark and designated verifier snark are comparable. Is there any inherent gap between the two types, the two variations? And that's the main purpose of this work. We try to fill this gap by defining an intermediate model. We define an intermediate model, we call it SPARC, or succinct publicly certifiable proof. And then we show how to construct this type of, how to construct a SPARC based on threshold, fully homomorphic encryption, homomorphic signature, and designated verifier snark. And then we also generalize it into proactive setting that I will explain all these three items in more detail in the next slides. So let me begin with the model we defined for SPARC. So in our model, we have a committee of size n, where this committee is holding a secret. So each committee member has a share of this secret. And this secret is such that it allows the committee members to certify a proof. So what do I mean? We assume that we have a prover as before, it just publish a proof. So this proof pi0 is not publicly verifiable. But then we have a committee that is sharing a secret. And this committee, by looking at this proof pi0, they generate a certificate and then collecting some threshold number of these certificates, some valid certificates. If we combine these valid certificates, some threshold number of these valid certificates, we can verify publicly if the proof can be accepted or not. So at the beginning, as I said, the prover just publish a proof pi0. Then we have committee members that each generate a certificate. And now, by collecting a threshold number of these certificates, we can verify the proof. So more formally, a SPARC is defined as follows. We have a setup that takes as input NP relation and threshold parameters D and N, and output some public parameters and a set of verification keys for each committee member. Then we have a proof algorithm that takes a statement and a witness and output a proof pi0. Pi0 is just a standard proof. You can see it as a designated verifier proof. And then we have part cert algorithm that takes one of these secret shares, SKI, the statement, and this proof pi0, and outputs some partial proof or partial certificate pi, which is coming from the certifier I. And then there is an algorithm that verifies if this certificate is generated correctly or not. And at the end, a set of these certificates pi combined together can verify the proof. Output a 0. We have a verification algorithm that takes pi0 and a bunch of these pi and outputs 0 or 1, depending on whether the proof should be accepted or not. And then we define several properties for this primitive that I am skipping in this presentation, but they are mostly standard properties that we know. Let me explain a bit about the construction and intuition behind the construction. So the construction is from threshold fully homomorphic encryption, homomorphic signature, and designated verifier snark. So the idea is that in the setup, we just run the key generation of a designated verifier snark. By key generation, I mean an algorithm that output a CRS and the secret key corresponding to the CRS, the trapdoor. So I call it here EK and VK, meaning evaluation key and verification key. And then we also run the key generation of threshold fully homomorphic encryption. We get a key pair. And then the public parameters are just the evaluation key of the designated verifier snark, the public key of the TFHE, and a ciphertext, which is the encryption of the verification key, the encryption of the designated verifier snark verification key. And then we secret share the secret key of the threshold fully homomorphic encryption and give each share to the corresponding certifier. So the prover just run the designated verifier prover, given a statement and evaluation key of the designated verifier snark, and the witness, it compute a proof, which is designated, it can be verified by a designated verifier, not publicly. And then we have part cert, that is the algorithm that each certifier run. So the certifier run the TFHE evaluation of the circuit C on ciphertext CT, which is part of the public parameters. So what is this C? The C is the circuit corresponding to the verification of the designated verifier snark by hard-coded parameters, a statement, and the proof pi 0. So only the verification key of the designated verifier snark is unknown here. And each party compute the ciphertext and then run the partial decryption on this ciphertext and get some output YI. And also, it also compute a signature, a homomorphic signature that certify this computation is computed correctly. So the proof pi I, the certificate, consists of a partial decryption and a homomorphic signature. And then part cert verify, just verify the homomorphic signature part of the proof. And then the verification is by combining D out of N valid YI, proof YI, and by combining them and running the decryption algorithm of the threshold fully homomorphic encryption, we can verify the proof. And the important thing is that all these primitives can be constructed based on lattice assumptions, such as LWE, which means that now we have a construction of post-quantum spark from lattices. And because this type of, because a spark can be seen it looks very similar to publicly verifiable snark with one more hub in the middle, that is the committee members. So it's somehow a middle ground between designated verifier snark and publicly verifiable snark based on lattice assumptions. So far I was only considering a static committee, but in applications we usually have a proactive committee, meaning that in round one we have a committee, and then in the next round the committee change, in the next round. So in each round, after every several round, we have a new committee members. And for that, we introduce a new notion. We extend and generalize our notion of a spark to proactive spark, where in this case the committee can change dynamically. And then we also extend our construction in previous construction into proactive case. But in the new construction, we also require circular security for the underlying fully homomorphic encryption. So to summarize, we introduced this model of succinct publicly certifiable proof that that provides public verifiability. And then we give a construction based on threshold fully homomorphic encryption, homomorphic signature, and designated verifier SNAR that all can be instantiated by lattice. And so it's post-quantum. And then at the end, we also extend the construction into proactive Spark, where the committee is not fixed anymore, and it can dynamically reshare the secret to the next committee members. So that was my talk. Thanks for your attention. And for more details, you can also check the full version on ePrint.
Thank you, Hamid Reza. And do we have any questions for Hamid Reza?
Anyone, any question, any suggestions? Okay. There is one question from Professor Gordi.
Does your work, meaning the model and the derivations, have anything to say on the cardinality of the committee, upper limit, lower limit?
Yeah, I think there is because of the one constraint we have for the FHE construction, it should be a constant size.
Constant size, but no indication on what that constant is, or there is an indication?
I don't think there is any condition, and just any constant, I think it should work.
I see. Okay, maybe
I mean, independent of the size of the whole
card. Okay.
User, yeah.
Independent. Okay. Nice presentation.
So do we have any other questions? So I don't see there are any online questions. And from live feed, do you have any more questions?
No, not from this side.
Just a continuation of the previous question that on the number of committee members. So in the dynamic setting, this number can change, right?
Right, exactly. But there is no issue from this aspect because the resharing is just, we are using some proactive secret sharing schemes that the number of shares, the number of parties that for which we share the secret, it's not fixed. Okay. So in round one, it can be N1, in round two, it can be N2. So
in that sense, the number can change if committees change in the dynamic setting at least, right?
Yes, exactly.
Yeah, I mean, I found the paper very interesting. Of course, the proofs were very difficult to verify. I must have spent almost 2 weeks on the paper, and I'm still not sure if I got all the proofs, but very interesting paper and something I want to read more on. So thank you for providing the link to the full paper. Does it have more than what is in the published paper?
Yeah, I think because of the page limit, we skipped some. I mean, we refer the reader to the full version for many details. So I think it's more. It has more than the submitted.
Okay. So looks like there are no questions, and we are anyway almost close to 7:30. If the online viewers they have questions, they can of course go to the Google Talks for these 3 speakers, and you can ask questions one-to-one with them. And that's it, I think. This concludes all the presentation sessions of Indocrypt, and there will be a valedictory session which will start just right about now. So thank you, Hamid Reza. Let's thank all the 3 speakers, all the chair. Thank you.
And a special thanks to the session chair, Professor Vishal and Professor Abhishek, for joining with us. Please do join us to the valedictory session of the conference with Dr. Shweta right from the venue. Thank you.
If anyone you wants tea or coffee, you can just quickly can come 5 minutes.
So please let me know when to start.
So please start.
So good evening, good morning, and good afternoon to everyone as per their time zone. We have reached the end of the 22nd International Conference on Cryptology in India, 2021, Indocrypt 2021, that is organized by LNM IIT in association with R.C. Bose Center of Cryptology and Security and the Chatterjee Group, Centers for Research and Education in Science and Technology, Kolkata. This conference was executed in the hybrid mode. I, Shweta Bhandari, Assistant Professor in the CSC department here at LNM IIT, on the behalf of the Institute and the entire organizing team, heartily welcomes the Chief Patron and the Director of our Institute, Professor Rahul Banerjee, General Chair, Professor Ravi Gorthi, Conference Chair, Professor Abhishek Adhikari, who have joined us virtually, Professor Bert Prinil, and Professor Ralph Kuster. They have also joined us remotely. Organizing Chair, Professor Jayaprakash Kar, all the supporting team members, and respected participants. We have successfully executed the conference with the help of our eminent speakers from all over the globe. My special thanks to Professor Adi Shamir, Professor Maria, and Professor Karthike for accepting our invitation and delivering interesting talks in this particular event. I hope that through this event, we have provided a great platform for all the faculties, researchers, and students who have attended the session to upgrade their knowledge in the area of recent emerging technologies in modern cryptography. So now I would like to request our Honorable Director, Sir, Professor Rahul Banerjee, to enlighten us with his inspiring words. Please.
So very good morning, good afternoon, good evening, wherever all the participants, experts, and well-wishers are. I don't think that I have anything to enlighten an enlightened set of participants and experts here. I would simply like to thank each one of them for the contributions that they have made to this conference. People who have conceptualized and made this conference possible, people on ground who have coordinated amongst themselves, whether from logistics point of view or elsewhere. A very major amount of effort has also gone into paper reviewing process, because it is quality of a conference depends on the quality of the papers that we accept. And even the papers which do not get accepted, quality review as goes to those papers and their authors, helps those authors to improve upon and probably present it in a better way, more complete way elsewhere. So in this ecosystem, I do see many high quality presentations. I have attended only 2 sessions in person and 3 sessions out of the sessions that we have had, other than the say keynote or talk sessions, in virtual mode from my office. And I did like quite a few of the things that I learned from that. There are pieces of work which are still works in progress, but all that said, that is what a conference is all about. So I'm very glad that an effort from all the people here, elsewhere, organizers, thinkers, think tank behind Indocrypt, it has come to a fruitful conclusion today, but probably just only to stay a little and come back again next year, wherever Indocrypt comes as its venue, find its own petition. Thank you very much.
Thank you, sir. Sir, just a minute. Thank you so much, sir, for all the back and support that you have provided. So now I would like to request our organizing chair to present the memento to our chief patron. सर वहीं पे सब वो कैमरा हम Thank you, sir, once again. Now, I would like to request our conference chair, General Chair, Professor Ravi Gothi, to say a few words.
Good morning, good afternoon, good evening. A conference for researchers and academicians is a kind of festival. And when the festival comes to an end, there are a mixed bag of emotions, all right? Things learned, networks made, friends made, plans for future research, and many more. On behalf of the organizing team, I thank profoundly the invited speakers who were gracious, the PC chairs, PC team, and the steering committee who stood behind like a strong backbone. And many of these organizing members, all the organizing members, starting with Professor Jaiprakash Kar and his entire team of faculty members, students, postgraduate, undergraduate, but for them, things wouldn't have been. And if at all there is any lacuna anywhere, kindly pardon us, and we will try to definitely improve for the next time. And so, wishing all these who participated in various different ways as delegate, paper presenter, invited speakers or reviewers or organizing team members, enjoy the evening and possibly you all meet again next year. Thank you.
Thank you. Thank you so much, sir, for all the support. Now, I would like to request our conference chair, Professor Abhishek Adhikari, who has joined us remotely, to say a few words.
Thank you, Sweta. It's really a great pleasure for me to be here. It's really bad that I couldn't join there personally, in person, but certainly I enjoyed the whole thing, joining there remotely. So the point is, in spite of the situation, adverse situation that we are all facing, we could manage it in a nice way and in a grand way. And the thing that I must say that it's really a very good teamwork. So starting from program committee members, we all work really hard because the duration of paper reading was, paper reviewing was very less, but still in spite of that, all the reviewers, they did their 100% to make it a success. And also I must say that organizing a conference in a hybrid mode is really around twice for organizing a conference in a hybrid mode, because you need to take care of the venue as well as the online mode. And as a team effort, I think that we did it quite well, and we learned many things from here. And we started with our journey from a pre-conference workshop, so organized by Vishal and his team. And then we had a tutorial by Dan Bunstein. So we must thank all the speakers over there. And then we have an invited talk in the conference. And I must say thanks to all the speakers. Sweta has already given thanks to them. And of course, we should not forget that the event management team, Nana and Ninni and their team, they really did well, always with all of us. And thanks a lot for making it a success. It's all about the team. Thank you.
Thank you, sir, for all your guidance, all your support, and all-time availability for meetings and all. Thank you so much. I would also like to request another conference chair, Professor Bert Preneel, who has also joined remotely, to say a few words.
Thank you very much. It has been a great pleasure to be part of this community. And as a scientist, I'm really happy with the profession I chose, because that's really amazing. In our profession, we can actually travel the world and interact as a community. In many countries, people from all over the world can collaborate together and make progress and achieve success. And I'm very pleased to see that also India is a full member of the National Cryptographic Community, and that we're working together very nicely to advance cryptology. I always like to come to India in person, because to me it's always a very enriching experience. I meet new people, I learn many things, and I really regret that I couldn't make it in person this time, but I definitely hope that in one of the future occasions I will be able to attend Indocrypt again. And so I want to join also Abhishek in thanking everybody who made this possible, because this is a big team effort of both people taking care of program organization and also the people you don't see behind the scene, technical staff who make this all work smoothly. So thank you all for collaborating, and hope to see you at the future Indocrypt. Thank you.
Yeah, thank you so much, sir, for having trust in us. I would also like to request the conference chair, Professor Ralph Kuster, to say something.
So thank you very much. Let me second what Abhishek and Bart said. So this has been a very nice experience. I was impressed really by how smoothly the hybrid mode was handled by the local organizers. So a big compliment, because this is doing like two jobs at the same time. And so it was a pleasure to work also with my colleagues, Abhishek and Bart. So, and also special thanks to Abhishek, because he has been the interface between the local organizers, and he hold all strings behind the scenes and make sure in particular that when the conference was running, that everything goes smoothly and everybody is informed. I think we had a very enjoyable program. So I learned a lot. We had many great talks. Of course, we had several esteemed invited speakers and tutorialists whose presentations I found very inspiring as well. So thanks to all authors for all attendance. Thanks to local organizers again, including the event team. Fabulous job, LMIIT, for having us. All the session shares, certainly the PC, who did also a big chunk of the work, and again to my co-chairs. So for those at the venue, have a safe trip home. I hope I have a chance at some point to meet you all in person. So bye, everybody.
Thank you. Thank you for all the nice words. Now I would like to open the floor for the participants who are present at the venue as well as who have joined us virtually. If anybody would like to share their experience, most welcome. Yes, anyone?
I just want to make an announcement that the next Indocrypt will be held in Kolkata and will be sponsored by TGC Crest. And we are hopeful that it's going to be an offline mode. And therefore, we hope to see you in Kolkata next year. Thank you.
Yes, anybody who joined virtually would like to share anything? I think some of the students at the back would like to share something. So if somebody can hand over the mic.
It's really nice for us to be here in this great event, and it's really nice for us to, first of all, this gives a lot of motivation for us to continue in this field, as we were like very basic right now in cryptology, and it will give really motivation for us to get into a really new heights in this field, because here we didn't till now, whatever the exposure we are right now, it's going on in this direction. We really got, and we have seen almost the legends in this conference with our own eyes. So it will give really motivation for us. I think we hope we will be participating in much more conferences like this, and we'll hope and thank you for all the LNMIIT and for all the organizers, and for giving thank you so much on behalf of all the students and participants from our side for giving a chance for us. Thank you so much.
Your name, please?
My name is Sai Baba.
Thank you. Thank you, Sai. Anybody else? Okay. Thank you. Thank you to all the participants. Now, I would like to request.
Just a minute. Some backstage members are also present. So, may I request Dr. Bhupender Singh, maybe, if he wants to say something. Vishal is also there. Dr. Ali is also there. Anybody? If you like.
Well, thanks all for such a great program. I can maybe give you a small report on the workshop that Abhishek mentioned. So in affiliation with Indocrypt, we also organized this post-quantum cryptology workshop, which some or many of you attended. It was also a very successful workshop. We had like 14 hours of talks on various post-quantum cryptology topics. And this was focused on the NIST finalists. So NIST is doing a competition on that. So The talks were from five finalist teams on different topics. So yeah, there were I think registrations were like more than 450 registrations. So it was pretty successful, we believe. Yeah. And we'll put up the videos and provide a link to the YouTube channel, and we'll send it out. So it will be there.
And also, a few other participants were asking for slides as well. So could you please make it also there?
Yes, we'll try to make the slides also available, but videos will certainly be available soon. The videos are getting processed. So some editing will be required because they are all in one huge bunch.
Yeah. So maybe Dr. Ali, would you like to say something? Okay, then maybe Dr. Shiny.
Yes, good evening, everyone. So I would like to thank everyone, and especially Professor Jayaprakash and Abhishek for coordinating every day smoothly and making sure that everything goes smooth and as per the plan. Indocrypt is a very reputed conference, and we are honored that LNMIT was able to organize it successfully, and we thank the team for giving us this chance. We are sure that the event will be inspiring a lot of researchers who joined from ISI Calcutta and from LNMIT, and we will be able to produce great results in this field. Thank you, everyone.
Thank you. And Dr. Bhupender Singh, are you here? So please, if you would like to say something.
I'm here.
Okay, please go ahead. Your final conclusion, maybe.
Oh, thank you. Yeah, as Professor Abhishek Adhikari told, organizing conference in hybrid mode is very difficult, actually. I could feel that, but LMNIT proved they can do, actually. In the pandemic situation, when most of the people are in remote location and some people are in the campus, managing this is very difficult. Somehow that was a very good, actually. Thank you for such. And sometime one day we had some problem with Adisami's talk. That day I was also got confused. What happened? I'm not able to listen. Then I messaged Professor Abhishek Adhikari. Then he told, "Yeah, no, that was the connection." So online mode has advantage as well as disadvantage. Both are there. So hopefully next Indocrypt will be fully physical mode in the TCG crust, and hope to see you all there in 2020 December. Thank you, Professor Adhikari.
Thank you, Dr. Singh. And I'm sure that next year we'll surely have Indocrypt in Kolkata, where I'm currently in. So welcome you back there. And it will be in 2022. And I'm sure that we will all be there with a good health and all. Thank you all from my side.
Professor Adhikari, some of them have shared their experience in the chat box. If you could read out for us.
Okay. Dr. Ali says, thanks to all organizers for organizing excellent event Indocrypt 2021. Thank you, Dr. Ali, for sharing with us your valuable comments. And nothing else I could see here. Yeah, so thank you.
Okay, thank you. Thank you so much. And thank you all the participants, all the team members who have helped us to make this event successful. So now I would like to request our organizing chair, Dr. Jayaprakash Kar, to deliver vote of thanks to everyone.
Good morning, good afternoon, good evening. Now I would like to take this opportunity to put my gratitude into words. First of all, I would like to thank Almighty God for making this event a great success. On behalf of our LNMIT as well our the Center for Cryptography, Cybersecurity and Digital Forensic and all organizers, I would like to extend my heartiest thanks to our all honorable chief guest, Professor Bimal Rai, for your presence in these functions, for having trust in LNMIT and providing this opportunity to organize such an event. Wholeheartedly, I must thank our director, sir, Professor Rahul Banerjee, for his continuous support and guidance for organizing such event. Thank you, sir, for assisting and encouraging all of us. Thank you, Professor Abhishek Adhikari, Professor Brad Pennell, Professor Ralph Kolster, Professor again Rahul Banerjee, Professor Ravi Gurti, he is the general chair of this conference, for your presence in this event. We have been fortunate enough to get these eminent speakers throughout this globe for accepting our invitations and embrace this event with their knowledge. Thank you all. I thanks all the participants for their presence in this event. Everyone is so supportive and cooperative. Thank you for showing your trust in us. Thanks for all support for all faculties and lab staffs for making this event successful. My special thanks to organizing team, Dr. Sveta Bhandari, Dr. Mukesh Jadon, Dr. Nilotpal Chakrabarti, Dr. Paulomi, Dr. Saurabh, Dr. Mohit, Dr. Preeti Singh, and all the volunteers. Mr. Vikas Vajpayee, Dr. Sandeep Saini, Dr. Gaurav, and all these research scholars, Nancy, Mansi, Bhupens, Srushti, Parul. Also thanks to all the IT teams, support teams, Mr. Mukesh Sarmaji, Mr. Rakesh, and the CSE Junior Assistant, Mr. Abhishek. Thanks to Mr. Shivam Maheshwari, who is involved in designing this website. And whenever I called him, even in the night, 10 o'clock or 11:30 or 11 o'clock, any times, he picked my call and changes this website time to time. Showcase event, I very much thankful to the showcase event, Naina and Naini, for making this event great success. I heartily apologize if I have forgotten to mention any name. It was very challenging to organize this event in hybrid mode. Many of these also participants and those who have joined in this online and this in this venue, also they are accepting. So really, it is a very challenging, and always I was updating this pandemic situations in what way we can proceed this event. It was very and again a heartfelt congratulations to all the members of the organizing team and the volunteers for your hard work, which has made this event a memorable one for all of us. Now, thank you all of you, and I am giving Sveta that. So I am very much thankful to all our sponsors, like your thankful to Archivos Cryptology and Securities, then the TCG Crest, NB Agents, DRDO, Microsoft Research, as well that the other some few funding agencies still they are processing, and also thankful to all our funding agencies.
Thank you. Thank you, sir. Now I would like to request everyone to stand up. We will conclude our event by national anthem.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड़ उत्कल बंगा विंध्य हिमालय हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
Thank you so much everyone, and have a good day ahead.